Yeah, hello, sir. Good morning. Yeah, hello. Sir, you're not audible, sir. I
Yeah.
think, yeah, we can hear you.
Yes. Sorry.
Yeah, it's good morning, sir. Yeah, welcome.
Yes. Good morning. How are you?
Good, sir. Thank you. We'll start the session shortly, sir.
Yes. Yes.
We're
Sure. Sure.
waiting for a few more minutes. Yeah.
Yes.
Do you
Yes.
would you like to share your slide and just check it?
Yes. I can do that. Yeah.
Okay, fine.
So let me share the screen.
You can do that present now at the bottom.
Mm-hmm.
At the bottom of the screen, you see a present now, sir.
Yes. Yes.
Yeah, you can do that. Present now, and you can share your screen, entire screen. Three
Okay.
options are there. Yeah, present your entire screen and then open your PPT.
Yes. Yes.
Okay.
Actually, I have to log out and then again log in. So I will
Okay,
join
fine. You
in
can do
two
that,
minutes.
sir. Yeah, no
Yes.
problem. Yeah.
Okay.
We can see your screen, sir. We can see this.
Okay. I have some audio signal to play. I hope
Do you
it
want
will.
it might work. Do you want to
Okay.
try it now?
Yes, I can try it now. Yes.
Okay, sir.
So, are you able to see my screen now?
Yes, we can see it well.
Okay.
Yes, sir.
Yeah, we did have your caution in mind as we were, as best we could, while doing the reports.
We
So let
can
me
hear
hold
it,
on
sir.
to this for a minute because I want to be talked out of it.
Yes. So, does it play the audio?
Yeah, it's playing the audio. We can hear it.
Okay. Okay. Good
Okay,
then.
thank you. Yeah. Okay, sir.
Yeah. So, we can start any time you are ready.
Okay, fine. So maybe in few minutes. Yeah.
Yes. 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 Sure.
Okay.
Good morning, sir. So, shall we start or shall we wait for some more participants to join?
Yes, I am ready. But if you generally wait for some time and many more can join in, we can wait. Not an issue.
Okay, sir. Good morning, all. A warm welcome to all the participants out there. Today, the day 4 of our 6-day AICT sponsored virtual STTP program. The first session for the day we have it as Desire for Speed, Quest to Bridge the Gap Between Human and Machine by Dr. Neeraj Sharma, who is a postdoctoral researcher at IISc Bangalore. Dr. Neeraj Sharma is a postdoctoral fellow at the Department of Electrical Engineering, Indian Institute of Science, Bangalore. Prior to this, he was a postdoctoral fellow at the Department of Psychology, Carnegie Mellon University, Pittsburgh, and a visiting researcher at the École Normale Supérieure, Paris. He holds a PhD from the Department of Electrical Communication Engineering, IISc, and his research interests include problems at the intersection of brain science and engineering. His contributions are in the areas of speech signal processing, auditory neuroscience, and machine learning. We welcome you, sir, to start the session.
Yes. Hi everyone. Thank you very much for that nice introduction, and thank you also for this opportunity to present in this forum. So I'm glad to get this opportunity. So what I'll do is I will go through my presentation, and if you have any questions in between, you can unmute your microphone and ask. Is that an option?
Yes, sir, they can do that.
Okay. Yeah. Or else you can wait till the presentation is over, and then we can discuss on any of the slide you have any question on. Feel free to interrupt anywhere in between. It will be nice to have this more of a kind of a discussion than only me talking. Also, as I am also virtual, so it's good to make it more interactive. So shall we start then? Okay. So again, I'd like to introduce the title first. So the title of the talk is "Desires for Speed in the Quest to Bridge the Gap Between Human and Machine." And to explain why this title is here for this talk. So I'll first try to give an introduction for this. So let's see how have engineering fields evolved over time. And this is a difficult question, right? Because we don't know which engineering field started, and there has been a lot of progress since past 200 or more years. But we have started writing books since more than 200 years, and what we can do is we can go back to these books and we can try to count the number of times these names of these engineering fields have occurred in different textbooks. So what you see in this plot is such a data where the x-axis is the years, time in years, and the y-axis is the occurrence frequency of these words. So these words are like computer science, civil engineering, mechanical engineering, electrical engineering, and electronic engineering. So I have only handpicked a few of these engineering fields. Sorry if your field is not there in this, but this is more to give an idea that how engineering fields have evolved over years. And you can see that not to our surprise, the very first field has been civil engineering, which started long back since we needed bridges, we needed roads, and we needed cities. So civil engineering started very early, and as we started gaining more understanding of physics and various other scientific aspects, mechanical engineering started to come into picture. It started to gain a prominence, and it started growing, right? And then as we started knowing more about atoms and electrons and other aspects, electrical engineering started, and it also started getting prominence there. And you can see that after electrical engineering, all the fields were growing, right? And in sometime in around 1950, electronic engineering started getting pace. And if you think about it, this holds because there was semiconductor invented, and semiconductor devices started to be built, and mission to moon was launched by USA in around 1964, and there was a big rise in semiconductor industry since then, and so electronic engineering started getting pace. And something further more interesting happened after electronic engineering, because computer started coming in prominence. You can see computer science started gaining pace, and and it has gained a tremendous pace. If you see the occurrence frequency, there are lots of books written on computer science, and there has been a steady rise. But you can see that after 2000, there's a drop has started in computer science as well, and this drop is also there in other engineering fields also. So every rise can also feature a drop, right? So that's not surprising. But what I wanted to illustrate here is that there has been an evolution in how engineering fields have come into picture. So each field has gained something from the previous one, and a new area of engineering has started building on what was existing on past. And how this has started is we have a desire for comfort, and we start understanding more and more of physics, and we start applying mathematical modeling to different physical systems, and we also get a desire to convert the theory to practice. And this is how engineering comes into picture in daily life. And the benefits of engineering, I will, according to me, one of the key benefits has been the saving of time, or it gives us speed, because you can take an example of road, right? If there was no road, then we would have taken a long time to reach from point A to point B. If there was no vehicle, we would have taken a lot of time. If there was no mobile communication system, we would have taken a lot of time to communicate things. And if there was no internet, I would have taken a lot of time to come to the college there and give this talk. So engineering, one of the key benefits of engineering has been the ability to, it gives us an ability to save time, and also gives us speed in return. So is all working fine? Hello?
Yes, sir.
Yes, sir.
Yeah. Okay.
We are able to hear you.
Okay. So if in case there is no audio, just say in between. Okay.
Sure, sir.
So my screen is here. Yeah. So this has been the engineering fields have evolved over time, right? And if you see currently what is making impact, what we can see is there is a steady rise in topics or fields, subfields associated with computer science. And some of these subfields are like, you can see machine learning has been increasing in prominence in various books, and so is artificial intelligence, which is one of the key top theme of this school, right? And you can see that as machine learning and artificial intelligence have gained prominence, there's a prominence of data science also coming into picture. So this is interesting that we are trying to create a science based on data, right? This was something which people would not have imagined 30 years back. Like computer science would not have been imagined in 1900s, early 1900s or 1850s. So we are getting new topics of interest, and you can see that there's a rise. So we are having a good theme of this school, which is AI, and one of the major impacts of AI, which has also contributed to this rise, is that there are many areas where AI is being considered as an impactful theme, or a research of impact making tool, you can say. And these areas are related to our daily work activities, like you can see travel, transport, retail, telecommunication, banking, aerospace, electronics and semiconductors. So you can pick any field, and there'll be, and you do a Google search, and you will it won't be surprising if you find that somebody is trying to use AI for that area. So this is something which is happening with AI, which didn't happen very much with some of the other fields. Maybe it would have happened with electrical engineering. We don't know. It would have been in 1900s. But if you look back 50 years or 30 years from now, this AI looks like one of the key topic which is impacting various disciplines and various practical applications. So what is intelligence? And so if we do a wiki on this, we'll see that the ability to perceive or infer information and the ability to perceive or infer information and to retain it as knowledge to be applied towards adaptive behaviors within an environment or context, right? So, and if you think about this definition, let's read it once again. So, intelligence is the ability to perceive or infer information and to retain it as knowledge to be applied towards adaptive behaviors within an environment or context. And you can think about yourself now. Like suppose you travel to a new state or a new country, and suddenly you are surrounded by a new environment, right? And what you do is you infer from your past information or past knowledge to adapt to the new behavior. And if you're able to navigate through that new environment or new ambience, that is something we say as intelligent behavior, right? And many of the species, including humans, show this ability. And you can see that a baby, in fact, a newly born baby also shows this ability within 1 year of his or her birth. So this is a one definition of intelligence. There can be many other definitions, and this is also an open topic that what defines intelligence. But we can all agree for this talk that this is something we can call as intelligence, right? And so what is artificial intelligence in this framework? By artificial means that we want to create it in a man-made way, right? It doesn't exist in nature and we want to create it. And this has been a human curiosity to create artificial intelligence beings. And this also goes long back in the 1850s when Charles Babbage was trying to introduce mechanical engines which can compute. And there have been several lines of work in this topic of artificial intelligence. So it's not a new word of 20th century. It was proposed in some time back, and there have been a lot of work on this topic in 1940s as well. And the field was referred to as cybernetics, and slowly it has evolved over time, and we are here now today. So artificial intelligence in some way wants to mimic the definition of intelligence and want to create machines which have that ability, right? But this is a very challenging problem, and there has been some work which has shown signs of this possibility, but it is long way from now on. Like it may take more than 5 decades or more to get something like intelligence. So what people have tried to do, they've tried to divide this artificial intelligence area into 2 subfields. So one we can refer to as artificial narrow intelligence, and the other is artificial general intelligence. So in artificial narrow intelligence, we can define, there is a consensus that what we can achieve in this setup. We have some input and we have some output, and all we want to do is go from this input to output. An example you can consider is suppose you have audio and you want to get text transcripts out, and this is also there in this current Google Meet setup. Like there may be a caption tab somewhere, and if you hit that caption, my speech will be transcribed down as text, right? So there is an input data and there is an output. So it's a well-defined question, at least, that you have this input signal and you want to get this output signal. And similarly, the topics include, like, if you have a music playing, can you say what the song was or what the song is? And if you have an email, which is like which is a collection of words, can you say whether it is a spam or not a spam? So similarly, if you are navigating a website like Amazon, and based on what products you clicked, can you design your ads so next time the user visits the same website? So these you can see a common theme in all these applications, that you have an input data and you have an output data, and you want to say, can you predict the output from the input, right? So when you want to do prediction, you want to design a predictor. So to design a predictor, you have to learn what the relationship is between input and output. So for that, we need lots of labeled data. And once we have a huge amount of labeled data, we can try to design algorithms which can learn this relationship between input and output. And once it has learned, we can give it test data, and it will give us the output for the or the prediction. So this is referred to as artificial narrow intelligence, and you can see why we call it as ANI, because if you look up to the definition of intelligence, it is not matching that, right? We are not perceiving or inferring information or retaining any knowledge, and we are not adapting to new behaviors or context. We are just learning a relationship between this input and this output. So it is a narrow form of intelligence. And there has been a lot of progress in past 15 years on this topic especially, and that is the major and the major reason for the impact which is being hypothesized to other fields of applications. And if you come back to a more broader theme of AI, which is referred to as artificial general intelligence or AGI, that is what will take us closer to intelligence. And this is a topic which I'll not touch on in this talk. And if you looked at the literature, it is yet to be understood in much more detail and how it can be achieved. So what I hope this clarifies some things on AI, that not all AI is AGI, and a lot of AI, current day AI, deals with ANI, and a lot of hype which you see in news articles and many of the topics of research, it may very happen to be ANI instead of AGI. And but I will also say that there is a lot of wonderful research happening in AGI also, but we are far from the ability to mimic human intelligence. Okay. So we can look again at the question of why this sudden recent growth in ANI, right? And the reason for this is that there is lots of data now available. Once we have internet, and thanks to this plot again, which is the same plot we saw some time back, after computer science came into prominence, we had internet, and there's a lot of documented data being collected every day. We browse internet, and so this has given us a lot of data of different types. And we have also developed an open code share community like GitHub and other places, which makes us, which helps us to easily share the code. And once you start sharing the code, you start writing standardized codes and standardized ways to do things and ways to implement algorithms. And this has also been complemented by increased computing resources. Thanks to Moore's law, we now have very good computing power in our mobile phone as well as in our laptops. And there has been innovation in algorithms, especially in the field of machine learning. These algorithms were there 2 decades back as well, but now people have got easy accessibility to implementations of these algorithms. And once you start getting easy accessibility, you start innovating also very fast. So all these together have contributed to the recent growth in ANI. And just as as example, on the right, I am showing a confusion matrix in which you have an application where you want to classify 9 different kinds of sound. So these sounds are vowel, O, E, A, and cough, samples, cough, shallow, 2 types of cough and 2 types of breathing, and 2 types of counting sounds like 1, 2, 3, 4, 5, like that. And you can see that the y-axis is the true class label, and the x-axis is the predicted class label. So if we have a diagonal matrix here with all values 100 in the diagonal, then we have perfect prediction. So if you give me a vowel sample of O, I will be able to perfectly predict that the sound is vowel O. But now you see in the algorithm, we are getting an 88% classification of vowel O. And similarly, we are getting for cough shallow, we are getting a 45% classification. And you can see that cough shallow is being confused with cough heavy. So there are confusions here. And so this is an example that you can classify different kinds of sounds based on a training and test data. So you have an input data and you have output as these labels. So you train the classifier and you can achieve some sort of classification accuracy. So far, so good. And what has been the result of such a artificial narrow intelligence success is that there has been improved performance in different applications, and this has increased the expectation of what ANI can achieve, and there has been a desire to make sense of any kind of data you get. And some of these fields range from programming to communication engineering, robotics, computer vision, gaming, music, technology, and also medical science. For example, in medical science, if you want to take an example, people are trying to document a lot of X-ray images, and they want to learn some sort of mapping between this X-ray image and this disease. So the disease can be pneumonia or some other form of cancer. So given an input data and an output data, you want to see if you can learn this mapping through some machine learning algorithm. And once you can learn, you can predict, right? So you get an X-ray on your with you, or you click an image with your camera and you give it to the classifier algorithm, and it can do some sort of diagnosis. So that is one example in medical science. So like this, there have been various applications, right? And this is what has resulted in this sort of prediction you see on the right, that going from aerospace to banking to oil to travel, that AI will have an impact, and that impact is quite big. If you see how much it can impact, some fields it's going more than 100%. So that is very encouraging, and also something to worry about, because if AI starts to work so well, then we will have to change policies in how we associate jobs with different branches, and which fields people take for their jobs, and government have to rethink their policy making. So does anyone? So this is a broad definition of what AI is about, and how it relates to the theme of this talk, that is desires for speed, because we want, as human beings, we have a desire to save time, right? Because we have limited time, and so we have a need for speed all the time. And engineering fields give us that ability to do things at speed. And recently, thanks to the growth in AI, there has been a quest to bridge the gap between human and machine intelligence. So we can take a break here. So if anybody has any question, and then we can proceed to the next part of the talk.
Neeraj sir, we'll have the question and answer session at the last.
Okay.
Can
Okay.
we go on with the presentation, sir?
Yes. Yes. Yeah. So, so coming to this, having seen that AI, AGI, and ANI, what they mean. So, in this talk, next, what I'll like to do is give an example of how we have approached one topic of our research interest and frame it in some way as how we can identify that there's a gap in human and machine performance in this research topic, and is there a hope to bridge the gap between human and machine. And this topic of our research interest is talker change detection. So I do recognize that many of you in this audience may not be from speech recognition or speech signal processing field, because the theme of the workshop is more on AI and robotics and control. But I will like to give an insight into how we choose this problem and what is the problem and how we reach the solution. And likely this will relate to many of the topics you are also working in. And so if you have any questions, we can discuss at the end that how it will relate to some topic of your interest. And why I chose to give this topic here is because it relates to some kind of the ANI and the AGI, the two fields of ANI and AGI, and how we can bridge the gap between the two. So let's dive in to this. And this talker change detection is something we do very often, right? So this will also connect with all of you in terms of what activities you do day to day. So by talker change, I mean that when suppose you are listening to a TV debate and there's one person who is talking, and in the debate there will be multiple people, right? And if you are listening to a debate, you can easily notice when there's a change in the talker. When person A was speaking and the person B was speaking, there is a change in the talker going on, right? And this sort of change is also perceivable if you listen to the debate on a headphone where the video is not there. So just the audio signal is enough for you to detect that there's a change in the talker. So this is quite amazing that without looking at the face, just from the audio signal, you can say that there's a change in the talker. And this is something we got interested in, and we thought that we will try to analyze this further and how good are machines at this when compared to humans in this task. So with this, let me turn on. So this work is this is a joint work with three of my colleagues, Sobna Ganesh, who was at Indian Institute of Science and working as a project assistant, and now she is doing her PhD abroad, and Professor Sriram Ganpati, who is a professor in electrical engineering, and Professor Laurie Holt, who is also a professor at Carnegie Mellon University. So this work was done by me as a part of a fellowship I got from IISc and Carnegie Mellon University, and the name of the fellowship was a Brain Hub Fellowship. So let's start discussing about this. So talker change detection. So speech communication is more often than not a dialogue, right? So you rarely talk loudly with yourself. And so speech signal is generally a dialogue. It is involved with when one or two more, with two or more persons. You talk on a phone, or you talk with your students, or you talk with your family. So it's a dialogue. And listening and understanding a dialogue is not difficult for humans, right? As I already said that you can listen to a dialogue on headphone and you can easily understand what was being spoken and when talker change happened. And so we do figure out on a daily basis if there are multiple talkers in the speech signal, or are the talker taking turns, or when talker A was speaking versus when talker B was speaking. So these are referred to as talker turns. And are there variable duration of turns? Like, for how much duration talker A was speaking versus how much duration talker B was speaking. And is there a speaking style variation between the talker? Like I am speaking right now, and suddenly my speaking style can change, and that change in speaking style can give you an understanding of my health condition or my emotion. So these are all humans are very good at picking up from just the speech signal, and this is something machines have not been able to do that well. So this is some sort of a gap in human and machine performance. And this is also some form of intelligence we are missing in machines. So, and there are also overlapping speech in our conversations, and we as humans are able to also understand speech even when they are overlapping. So, to give an example of what machines can do in this, so what I'll do is I'll play a speech signal, and what you'll see on the bottom is the real-time translation of the speech to text using a IBM Watson API speech recognition system. So just try to see how good the machine is when in this translation. So this has some audio. So I hope the quality of the audio won't be that bad.
Yeah, we did have your caution in mind as we were, as best we could while doing the reports. So let me hold on the note of skepticism for a minute because I want to be talked out of it, which is that I think reading the book, there are two frames that coexist in it. And I would call one the easier frame and the other the harder frame. So the easier frame, the one that I found completely convincing and I want us to talk about is the one you just mentioned, Jim, which is America is not what you think it is from watching cable news.
Yeah. So if you notice how many talkers were there in this audio, so let's play again. Try to figure out how many speakers were there in this this signal. Was there one speaker?
We did have your caution in mind as we were, as best we could while doing the reports. So let me hold on the note of skepticism for a minute because I want to be talked out of it, which is that I think reading the book, there are two frames that coexist in it. And I would call one the easier frame and the other the harder frame. So the easier frame, the one that I found completely convincing and I want us to talk about is the one you just mentioned, Jim, which is America is not what you think it is from watching cable news.
Yeah. So if you noticed, there was only one speaker in this whole audio signal, right? However, if you see the output of this machine system, you can see it is saying there are three speaker 1, 2, and 3, and it says which speaker spoke when, and it is giving us a transcript of what the speaker spoke. So you can see that this example that the machine system fails at this aspect of detecting how many speakers were there, and there will be some errors in the transcript as well, but that is okay. The bigger picture I'm trying to give here is that it is able to it is failing to detect that there is only one speaker, but instead it is saying that there are many speakers in this conversation. So with this example, let's see. So it's a challenging problem for machine systems, detecting how many speakers are there in a speech signal. So it's difficult for machines, and we see that it hallucinates talker change, right? When there is no change in speaker, it is saying there's a change in speaker. So that's a sort of hallucination. So these all are making it hallucinate, like talker turns, variable turn duration, speaking style is changing of the speaker. If you notice, the speaker was stressing at some words. So when you stress, maybe the algorithm is thinking that there's a change in speaker. So all these are troubling the machine system. And if you see how the machine performance is for speech recognition system, you can see that in early 2000, the word error rate which refers to how many words are in error in the recognition transcript, was quite high. It was above 20, close to above 30. And over the past 15 years, it has steadily come down. Like it was coming down slowly till 2012, and after that there was a sharp decrease. And a major contributor to for this decrease has been the success in machine learning, especially the deep learning methodologies of how to do speech recognition. And you can see that there is a human performance also given on the bottom, which is a horizontal line, and the machine systems are still far from the human when it comes to recognition of speech. And this is something we need in robotics, right? So if you want human robot interaction to happen at a seamless pace, you want speech recognition to work at a very good level, which is a sort of limitations right now. Right now you have to press buttons, but people are able to replace some examples, some applications like now you get TV remotes which have speech recognition systems, right? So you can say switch to Star Sports or DD News and into the remote, and it will switch in the TV also. So, but you have to recognize that that is not intelligence. That is some form of ANI, artificial narrow intelligence. So, and in ANI itself, we have lots of challenges when it comes to speech recognition systems and these sort of talker change detection and these sort of examples. So this performance was for speech recognition, and if you see the machine performance in the ability to detect who was speaking in the speech signal, so there also the performance is is not very good. So if you see the performance, it is there is a metric there, derivation error rate, and the lower the metric, the better it is. And if you see this table on the bottom bottom right, you can see that the DER is close to 13%. So we want this to be as low as possible, and a low value will indicate that a machine system can identify in a speech signal who was speaking when. And this is something humans do very well, right? Because if we are not able to do this, we cannot talk in a conversation. Like you cannot identify when speaker A was speaking and when speaker B was speaking. So the whole signal will become confusing. So this is a machine system have a challenge right now. And if you notice Alexa and other smart speakers, so they only identify when a single speaker is speaking. They fail to identify when there's a conversation. So these are some challenges in today's world when it comes to AI or ANI. So conversational speech recognition, humans do very well. And so we know that we have some kind of baseline system, which is a human, which does speech recognition very well. So we can start to rethink about how we should make a machine system do speech recognition. So can we learn what auditory mechanisms are used by humans? So what is the underlying brain mechanisms which make humans do so well to recognize speech? And once we get that sort of understanding, can we model these mechanisms mathematically? And can we write algorithms which model these mechanisms? And hoping that someday we will be able to do this, then we can hope that our speech recognition systems can work as good as humans, right? So this can be one direction of work. This may not be the only direction to approach the problem, but looks like one possible direction, right? And if you look back to our previous plots, how civil engineering and how mechanical engineering came into picture, that we have to first learn some physics of the underlying systems we were trying to make, right? And once we start understanding some physics, we started building mathematical models to make use of those physics. And once we have mathematical models, we started implementing those models in practice. And then we get the bridges, or we are able to design cars, aeroplanes. So similar things can be given as a direction for doing AI. and is that you learn how humans do say different tasks, and you try to model those tasks mathematically, that how humans are doing. And once you are able to model mathematically, you start to implement it using algorithms for day-to-day applications. So this has been a key theme in AI or ANI, majorly in AI, trying to model human behavior and learn from human behavior, uh, uh, how humans do what they do. And if we get an idea how they do what they do, we can build mathematical models for that. So there are too many questions, open questions, when we go into modeling human behavior. And so in this problem, we have started with one uh, human behavior, which is talker change detection. So humans do this very well, as we'll see. So what we do is, on the listener side, processing conversational speech demands quick perception of talker changes to support communication, right? So this we already saw that if you want to do conversation, you have to do talker change detection. So human do this very easily. So because machines don't do, so we want to understand how humans do and what is the performance when it comes to talker change detection for humans and machine. Okay. So as an overview, so what we'll see is, we'll try to frame this problem of talker change detection. And once we frame this problem, we'll see how to collect data for this problem, and how to model the human perception for talker change detection. And we'll compare how the machine performance compare with human performance. And we'll summarize what we learned from this. Okay. So there may be, maybe you are seeing a new word, some of you, which is perception here. So perception deal with any, that how the human brain understands the sensory signals around them. So we perceive sound, we perceive images, we perceive smell. So these are sensory signals, right? And how human makes sense of these sensory signals is referred to as human perception. So there's another word also, cognition, used in AI, which is a more meaningful interpretation of these perception. So these are some terms which you will start getting familiar with as you go deeper into AI. Okay, so let's go further now. So before going to talker change detection, we can just focus on what is change detection. So our sensory systems are every day challenged with some kind of change perception, right? So like suppose I'm talking to you right now, and suppose my power goes out, right? So the bulb in my room will turn off. So I will immediately sense this change. So our brain is somehow very much tuned to detect changes in our environment, and this changes in environment are sensed through sensory signals, and these sensory signals can be image, or they can be sound, or they can be smell. And you would have noticed that you are very good at detecting some of these sensory changes, and we detect the change, and also we have an action to be performed in return of this change, right? Suppose a loud sound comes now, so I'll immediately I will stand up and go out of the room. So I have some kind of action already defined in my mind, that what I will need to if there's a change in my environment. So change detection is something the brain does very well, right? And it impacts decision making, right? Because if you are able to detect change very well, then you take decisions also based on that change detection. And the art of taking decisions is also referred to as cognition, what I said previously. And a number of past studies on acoustic signal domain have focused on trying to detect, trying to see how humans detect changes on tones. So tones are like these single frequency signals, like being. So these are tones, right? And similarly, you have noise, right? The environment noise, and you have other non-speech signals. So humans, so there are past studies which have tried to analyze how good humans are when it comes to detect changes in these simple sound signals. And surprisingly, we didn't find any work on talker change detection in continuous speech. So when we were starting this work, so we did a literature survey to see what is there any work on talker change detection, and surprisingly, there was not much work on this topic of interest. So it's so you can so this suggests that very often a simple question may not have a lot of research findings out there in the literature. And there are a lot of such simple questions around us every day. And as we start aiming to build AI, we have to confront these simple questions, and we have to figure out how good are humans at this, and how good are machines at this. And very often, then not, you will find that such answers don't exist. So based upon your interest, you may find that many such questions interest you, and if you get interested, I'd suggest you pursue them. So one such question for us was the talker change detection. Okay. So what we did is we designed an experiment to understand how humans do this talker change detection. So what you see here is a blue signal, and it starts at t equal to 0, and at t equal to tc, there's a change in the talker of that signal. Okay, so the first signal is spoken by talker t1, and after time tc, the signal is spoken by talker t2, and what we ask the listener who is listening to this signal on a headphone is to press a button whenever they think that there's a change in the talker. Okay, so you can see that in this example, the person has pressed the button at time tr, so which is indicated here. After tc, there's a time tr, and at the listener presses the button there, and we note down at what time the listener pressed the button. So the tr minus tc will give us the reaction time for this change detection by the human. Okay, so this is the idea in this experiment, that we want to document how much is the reaction time of the human listener to detect talker changes. Okay, and this experiment we did using a interface designed in computer, and the person comes into a room and they listen to such signals over a period of 30 minutes, and they give us the reaction time for some 100 such signals. Okay, so now we have data, right? We had our question that how good are humans at detecting talker changes, and we now have the data for that. So taken from some 17 human subjects, and we collect this data and we tabulate that data. So what data we have is whether human detected talker changes or not in every speech signal, and if they detected, how much was the reaction time for talker change detection. Okay, so with these two data set, so we go ahead. So now, before going into further details, we need to understand what kind of speech signals to play here, right? Because a speech signal can be of various kind. It can be of various languages. It can be of various accents, and those and various types of sentences. So what we did is we took speech sentences from from audiobooks, and one such audiobook database, which is also available publicly, is referred to as Libri Speech Database. And we sampled 5 different speakers or talkers from this Libri Speech Database, and these were all male speakers. And from every male speaker, we made 8 stimuli per talker pair. So what we did is we take a signal from talker T1 and another signal from talker T2, and we join those two, right? So now if we join those two, we have a idea of when was there a change in the talker. So the TC is known to us, right? The talker change happened at this instant. So we have a ground truth for this. So this that's why this was helpful. Creating the database this way was helpful for us. So now, so we need to understand that the different people speak differently, right? So this is what you see in these plots are that in plot A, you see that we have 5 different talker in the x-axis, and the y-axis is the pitch of each talker. So different talkers have different pitch, and different talkers also have different speaking rate, which is quantified as words spoken per second. So this is the listening test setup. So the listener sees a screen, and on that screen there is a sound plays, and they have to press the button. And if they give a right answer, they get a tick, and if they give a wrong answer, they get a cross. And like this, the trials continue. So there are 200 such trials, right? And the key idea of this experiment is to get the data of reaction time for every subject using this sort of setup. So now, how fast do the humans respond? Right? This is one question. So you can see here on this left plot. So the x-axis is the ground truth change instant, that is TC, and the y-axis is the response instant, TR. So you can see here that for let's see, if all these green dots correspond to a correct detection, which is a hit, right? And you can see that all these green dots have a higher value than the ground truth change instant. So TR is greater than TC, and this is expected, right? So you have a reaction time. You cannot immediately press the button as soon as there's a change in talk. So you take some time to respond, and that time varies between 200 to 1.5 seconds. Red dots here in this plot, and those red dots come before there's a talker change. So this corresponds to false alarms. So there's no talker change in the speech, but the listener felt that there is a talker change. This is something like the machine example we saw in the very beginning, where there was no change in the talker, but the machine was saying that there's speaker 1, speaker 2. So humans also do that kind of thing. And there are these blue dots, which corresponds to miss, that the humans didn't detect a talker change. And we call this a miss because that comes after 2 seconds of talker change happened. So this is interesting that most of the humans get green dots, detect talker change very well. And this is some kind of quantification of the performance. And you can see here that the false alarm and miss are quite low. They are below 15 for 17 subjects. So that is good. And this is the reaction time spread. And again, on the left plot, you see that we have subject index and we have the reaction time. So this is a box plot from shows us how much is the spread in the data for each subject. And you can see that all subjects have a mean reaction time for talker change, which is less 1000 millisecond or 1 second. And if you see the pooled reaction time, which is the histogram shown on the right, you can see that reaction time peaks at around 700 milliseconds, right? Talker change within first 700 milliseconds. So now what we can ask, the next question is, okay, humans are good at this task. What features change detection, right? So we have two signals. One is talker T2. So what we can do, we can extract some kind of features from talker T1 and talker T2, and then try to see how far are these features. So what is expected is that if talker T1 and talker T2 are very far in their perceived feature space, then we will detect the talker change very fast, right? So this is to understand this further, you can say that if I dog and I ask you the question that are these two different animals, then you will immediately press the button that yes, they are different, right? So your reaction time for change detection for this image is quite fast. But if I give you two images which are both cats, and I ask you the question, are they two different cats, different animals, then you may take some more time if the two cats are of different colors or looking different. And if the dog looks more like the cat, then you'll take further more time, or you may have also a false alarm for that. So what we can do is we can extract these kind of features from speech signal, and we can ask the same question that are these two speakers close or far in their feature space, and if they are close or far, how does the reaction time relate? So when it comes to speech signal, speech is a 1D signal if captured using a single microphone. And if you zoom into this speech waveform, you will see something like this, right? And interestingly, the speech signal, like many other natural signals, has a changing frequency content over time. And you can see this in the spectrogram that the frequency is changing over time. And 1 minute. Just give me 1 minute. There's some disturbance here. I'll come back in a minute.
Sure, sir. We'll wait. Dear participants, you can post your queries in the chat box, which will be displayed at the end of the session. Attendance link for the current session has been posted in the chat box. All participants, please fill up.
Hello?
Yes, sir.
Yeah,
You're audible.
sorry. Yeah, sorry for that interruption. Yeah.
No problem, sir.
So we are here that how do we analyze speech signals, right? So speech is a 1D signal, and you can see this. If you zoom in into the speech signal, you can see that there is a nice variation in this 25 millisecond segment, which is shown for the step 1. Right? And you can see there are some kind of oscillations in this signal. And so if we take a Fourier transform of this signal, and we see the energy or the magnitude of that Fourier transform, that is shown in this column image on the bottom, we can see there are this blue color horizontal lines, right? And these correspond to, this shows that there might be some high energy regions in this short 25 millisecond signal. And if you see further, these dark blue lines correspond to high energy in the Fourier spectrum. You can see that they're close to equispaced. These lines are equispaced. So that means that there's some kind of harmonics in the speech signal. And that harmonic is varying across time. So if you see this image across time, so what this plots, every column in this image corresponds to a 25 millisecond signal taken from the speech waveform. And you can see that harmonic variation is changing slightly over the time. And which harmonics are weighted more or less? So this whole thing makes the speech signal to have a non-stationary spectrum. And this is also the case with many other natural signals. And very often, if you take a signal in electrical engineering or any natural signal, you'll see that the spectrum of that signal will change with time. And the spectrogram is one tool which is quite useful to analyze speech signals, but can also be applied to many other kind of time varying or non-stationary signals. So you can see that now that speech signal has a time varying spectrum. It evolves over time. So what we do is we take these 25 millisecond segments and we extract features from these segments. And we extract these features for talker T1 and talker T2 speech. And then we collect all the features for talker T1 and talker T2 and find a distance between these features taken from talker T1 and T2. So that is what we do here. Okay. So these are our features. So we have like 9 different features which have acronyms such as fundamental frequency F0, MEL spectrum, MFCC, and spectrogram, like these features. And what question we ask is, on the left you see a matrix y equal to ax, and you can see this y refers to as reaction time, log of reaction time, that is your r. So we have a linear system of equation, r equal to dw, right? So r is known to us because we obtained the reaction time data from the human subject. So r is known, and d refers to as the features which we calculate, and w is the weight of every feature. Okay, so our goal is to find w, that is the weight of every feature. And once we find this weight of every feature in predicting the reaction time, we can then ask the question that which feature predicts the reaction time better. Okay, so that is our goal. And this is the result, that we have different features and we have different explained variance in computing, explained variance in explaining the data of reaction time. And we see that some features do very well. For example, the MFCC D and MFCC DD explains the variance in the data a lot higher than other features. And this same thing can be seen in the plot on the right, that our bottom x-axis is the true reaction time and the y-axis is the predicted reaction time. And you can see that our predicted reaction time is following the true reaction time, but for reaction time which are very high, it is not able to predict them better. But for low reaction time data, around 500 millisecond, it predicts it very well. Okay. So now what we see that humans are able to do this task very well. And we also saw that some feature distance can help us explain the human performance, right? So now what we can ask is, how good are machine at this task? So we give the same speech signals to the machine which the humans had listened to, and we train a machine system to recognize talker changes. Okay, and this plot shows how does the machine perform. So each of these traces, this orange, blue, and green traces, corresponds to machine system, and this cross mark corresponds to the human system. Okay. So you can see that all the human performance are below the machine performance. Like the false alarm and the miss rate for human, which is the cross here, is much lower than the machine systems. So this indicates that humans are quite good at this task, and machines haven't reached that kind of performance level as humans. So this indicates that there's a baseline difference between what humans can do and what machines cannot do for this problem. And this is something we started in the very beginning, right? We saw an example how good machines were there. So this highlights a difference between human and machine system, and we need this gap to be filled in. Okay. So yeah. So in summary, what we see is talker change prediction is easy for humans. And we see that the reaction time for humans is between 400 to 900 millisecond. And we also see that human perception for these talker changes can be modeled using some features. And we saw that machine performance is yet to beat humans when it comes to this task. So now we can ask the question, okay, we see that humans are good and machines are not that good at this task. So we have hope that machines can reach as good as humans. So what we can next do is, can we model the machine systems using human features, like the features which humans use? Can we train machine system with those features? So this is something we like to in go in future in this direction, and see if we can improve the machine performance using some of these human insights. So this was one example of trying to understand a human system and a machine system and see if there's a gap. So what will happen if this gap gets bridged? Suppose machines become very good at this task and better than humans. So what we will be able to do is, then we can take lots of audio data which is already there right now. Like as I'm speaking right now, it may be that my data is also being recorded at Google or some other place. So if machines are very good at analyzing speech, then it will be able to do this analysis in very short time. Like you give it a 1 hour speech and it can do the transcription and recognition of talker changes, everything within say 10 minutes. And this saves a lot of time for humans, because now how labeled data is being generated for speech systems is by human labeling. So humans listen to these speech signals and they annotate that this word was spoken there, this word was spoken there, and that's how they generate lots of labeled data for speech recognition systems. So if we are able to design machines which can do this task, then it will give us a lot of saving in time. And once we start saving time, we'll get speed, and we'll also start improving performance for machine system, because once we have annotated data available, then ANI, that is the artificial narrow intelligence, can be used to improve performance, right? So this is what relates to our introduction, right? So with this, I will like to summarize that what we saw. So in summary, we saw that there are lots of experimentation needed to understand how good are humans at something and how good are machines at some things, before even asking the questions, can machine do this task, right? So that is one thing. And to do these sorts of experiments, we need to train and test. We need to train, and for training, we need to collect data. We need to do some testing to see if it generalizes to unseen data, and we need to think that is our machine system biased or not? Because very often, what happens in machine learning or artificial intelligence system is that we train a system on some data, and we see that it's performing good on our test data, and we sell that system in market or apply that system. But when some people use that system for their own data, which is not the same as the training data, and they get weirdly different results, and this can create a lot of problem, because if we like, for example, you can see examples in Facebook or Twitter where fake news and all these things go around. So this is a result of less thinking in designing this system. Like, how should our training data be chosen, whether it's generalizing or not? Lots of proper testing should be done. So the next point is that we have to be aware of hype, that all artificial intelligence, wherever this acronym is used, may not be AGI, that is artificial general intelligence. It may be just ANI, that is artificial narrow intelligence. So there's a big fruit yet to be plucked, that is AGI, right? And we are still far from it as of now. And the future is beautiful in this area of work. For example, there are very nice papers written, and many of these papers have open source implementation available in GitHub, and there's a lot of data which is being labeled and also shared as open source. So if you have any idea or you want to try anything, you have a lot of resources available. So with this, I'd like to end the presentation, and I'd like to acknowledge Dr. Deepa for contacting me and giving me this opportunity, and all the organizing team for organizing this nice event. And if you have any more questions, you can ask me now, and as well as contact me over email. Yeah, and thank you for this opportunity. So we can now go to questions. We have 15 minutes, so we can have some discussion.
Thank you so much, Needed Sir, for this wonderful session. We'll now share the questions that we have received so far
Yes.
on the screen.
So shall I turn off my screen?
Yes, sir, you can stop sharing.
Yeah. Yes. Okay.
So I
Yeah, I
hope you
can
are
see
able
the
to that.
question. Yes, yes.
Yes, sir.
Yeah, so the first question is there a better speech recognition system of companies other than IBM? Yes, there are currently many better speech recognition system like Google, Microsoft, and if you go back to Google and just search the state of the art, the performance has started to improve. So maybe you are asking why we chose IBM for our performance comparison. So why we chose is because it is available in public domain for testing purposes, and it is one of the state of the art speech recognition system, and it has that option of giving us the results back to understand how the algorithm is working. So we chose the IBM speech recognition system. Yeah. So next question is how Alexa detect a single speaker? Yeah, so Alexa assumes that there is a single speaker, and so it is not going for detection of single speaker in straight away. It assumes that whenever it listens the speech, there's a single speaker, and if it is not able to recognize the speech, so that means it is noise, right? So if multiple people are talking, then it will assume that it is a noisy signal. So I hope that answers. So that's why you would have seen that if there's background no noise, it will do very well in recognizing what you're saying. So third question is, what are the different matrices that are used for comparing these systems? Or different metrics, okay. So one of the key metrics to compare speech recognition system is word error rate. So if you have a 5 minutes of spoken speech signal, what you do is you pass it to a speech recognition engine like the IBM Watson, and it will give you a transcript that is the sets of word spoken, and you can compare it with your own transcript of that same speech signal and count how many words had error in that transcript. So that is referred to as the word error rate of the signal. Okay, so the lower the word error rate, the better the system is. And as I showed in the plot that currently the word error rate falls close to 5%. So that is the state of the art close to. So the word error rate is one measure to compare the performance. But we have to be aware that word error rate is not the end in speech recognition, because you saw that if you go for talker change detection, there's a lot of error, right? In talker change detection. So talker change detection can be another measure for detecting the performance. Similarly, you can go for emotion recognition. Is the system able to identify what the emotion was in the speech signal? That can be another measure. So next question. So if I don't answer any of these questions properly, you can rewrite it at the end. I can take it again. So question 4 is, could you please explain the other research work in speech signal processing at ISC Bangalore? Yes, so in ISC there are a lot of speech groups, especially in the Department of Electrical Engineering. And these speech groups are working on speech recognition and also speech enhancement, and also trying to understand how can we understand the health diagnostic So using speech signal, like can we detect COVID-19 using speech signal? So this is one of the key. This is a key question which, if answered, can be very impactful in current times, right? Because COVID-19 is a lung infection, and speech signal is generated from the lungs. So you would have noted that you rarely inhale and speak. Whenever you are speaking, you are releasing air, right? And this air is coming from your lungs. So if there is any abnormality in the lungs, so that will reflect in the way you speak also. So the speech signal there will be slightly change in the speech signal, and the people are trying to see if we can use machine learning to classify whether a person has COVID or not based on their speech signals. Similarly, people are using cough signals and other kind of vocal signals to understand other health diagnostic like pneumonia or snoring. So can we detect some abnormality in the snoring using and sound speech signal analysis? And another aspect which comes in speech signal is in music. Like there are a lot of questions we can ask from music. Like, can you identify the singer? Can you separate different instruments given the music signal? So these are some examples of problems being addressed. And also, some researchers are in ISC are trying to understand how brain understands speech signals. So, like I gave you an example of talker change detection. So suppose you listen to a language you are not familiar with. Suppose you listen to suppose a Chinese speech. So can you detect talker changes in a Chinese debate? So it so happens that humans are actually good at that as well. So even if you are not familiar with the language, you can detect talker changes. But machine systems, if they are not trained on this, they may not work as well as humans. And so that is something also of interest to some researchers in IC. Yeah. So coming to question 5, can we create basic speech recognition system using languages like Python? Yes, we can create, and there are also open source tools available which use something called Kaldi to design speech recognition systems. So please carry your interest forward and do Google on speech recognition system using Python. There are nice blog and articles said to try these things out. Yeah. And there's a need also for this, because if we want to make speech recognition being used in India, we need it to work for different languages, different accents. So we need to develop these in languages like Python so that people can build it and test it and get familiarized, and then only industry will take it up, right? So question 6 is current chatbot solutions are narrowly focused on specific areas. What is your opinion on that? Yeah, so this is the limitation of ANI. So you can only do as good as you have data on. So if you don't have data, then you have to limit your applications to some specific words, specific topics. So that is the limitation which reflects in chatbots, that they are domain specific. So we need more data and we need more algorithms. We need to understand how humans do these tasks. So then only we can make machines do it. So that is one line of thought I have. So question 7, has the job opportunities in data science area started getting saturated? And what can we do to get a job in the field? Yeah, so this is also a very relevant question, because as you saw in the news and also in the early slides that it is being predicted that AI will impact many fields, right? So there will be a huge market for people who know data science, and it's already being seen, like not only in engineering colleges, private and government engineering colleges, but also at higher education institutes like masters and PhD, that data science is being seen as one of the preferred field in job market. So we have to gear up to that challenge, and we have to augment our courses, our assignments, and our projects with some angle of data science. And it's not difficult, because if you see what I presented was a talker change analysis, right? And the question was very fundamental. But to answer that question, we need some kind of experiment setup. We need data to analyze, and we also need our traditional signal processing methodologies. Bringing in data science into the project, into the course, is a benefit, which helps to understand the subjects better, because now you can code very easily in Python. You have open source learning tools available. So these all are plus points, and this will help us to learn better things in future. So I think that the job opportunities, I don't think it is getting saturated. And what you may feel is saturation is maybe that it is no more increasing. And that can also happen in many of these hyped fields, that initially they will start with a big recruitment, but then they may saturate, and then again they may recruit. So that will happen. But there is a good demand. The demand may keep existing for some time. So question 8 is, kindly enlighten more on COVID-19 detection by machine language. Yeah, so COVID-19, as I said, is majorly a lung infection. So what you can do is, you can start collecting data of people coughing, and you store these sound signals, and you make a huge database of people who have COVID and they cough, and people who don't have COVID and they have coughed. So you have two data sets, right? Uh, Healthy people's cough sound recordings and COVID people's sound coughs recording. So now once you have these two data sets, you can train a classifier to detect if you can classify these coughs. So this is the high level view. If it works this way, then if it works, then we need to ask other questions, that it is generalizable, is it tested properly before releasing it into health authorities, right? Because if the data is biased, then it will create problems. So we have taken one such project in our group, and we are we are collecting this data. So we have created a website called koswara.isc.ac.in, and so what you can do is, you can log into that website. You can cough, and it will collect your cough sound, and it will ask you some questions, that are you COVID positive, are you healthy, what is the age. It will not take your private data, but it will only ask these metadata question at a broad level. And we are collecting such data, and we have like 1,000 participants, 1,500 participants right now, and so we are trying to see if we can detect COVID from these sound recordings. Yeah, so that is the answer to question 8. So yeah, so there are few efforts also in this direction. You can Google on that, COVID-19 using sound signals. So you will find more resources on that. Yeah. So in case I haven't answered any of your questions, so feel free to ask on the microphone if we have time.
So there is one more question coming up. Shall I read it out to you?
Yes.
Okay. With the ease availability of so much data, what impact will it have on the security of the users? For example, there have been news like Alexa collecting the personal data.
Yes. Yeah, so that is the challenge, that with more data collection, you need better privacy laws also. So people are trying to figure out answers to those questions, and while people haven't figured out, and while policy haven't changed, so this will keep coming up as a challenge, and we'll keep being confronted with such questions. Is the privacy being violated? So yeah, so that is a challenge. So it may be that in few years' time, privacy may be changed. The rules may change, so they may be limited to collect certain kinds of data. And until that law doesn't come into implementation, these things will keep bothering us.
Thank you, sir. Do we have any more questions coming up from the participants? You can unmute yourself and please ask your question. Okay, Neeraj sir, I don't think there are any more questions coming up.
Okay.
So thank you so much, sir, for such informative session and
Yeah.
for taking time to come to STTP and give us all these informations. On behalf of the entire Turkish management and faculty of Department of Electronics, I extend my thank you to you, sir.
Thank you. Welcome.
Yes, sir. Dear participants, we'll wind up with the session, and the next session will start at 11:10 a.m. Thank you
Thank you,
all.
Okay.
Neeraj sir. Yeah, thank you,
Thank
Neeraj
you.
sir. It's a very
Yeah. Thank
enlightening
you.
session. Yeah,
Yeah. Thank you for those nice questions also,
thank you.
and all the best with the training and the future talks. Yeah. Bye bye.
Thank you, sir.
Good morning, Manoj sir.
Morning.
Sir, would you like? Yes, Deepa miss.
Yeah, good morning, sir.
Good morning.
Yeah.
Very
Sir, welcome to the session, sir. Would you
okay.
like to try sharing the slides?
Yes, I'll do that.
Okay.
Can you see?
Yes, sir, it's visible.
Oh, okay, fine. So, shall I start or you have some?
So we'll begin the session by 11:10.
What time is it now?
So it's 11. Oh, sorry, sir. It's okay. 11:10 is starting. Okay, so we'll start the session shortly.
Okay.
Good morning, all. Welcome to the session 2 of the day 4 of our 6 days AICT sponsored virtual short-term training program. For this session, we have Dr. Manoj BS, who is a professor and head, Department of Avionics, Indian Institute of Space Science and Technology, IIST Trivandrum. Dr. Manoj BS had undergone his postdoctoral training at the University of California, San Diego after completing his PhD in computer science and engineering from one of the most reputed institutions, the Indian Institute of Technology, Madras. He specialized in the areas of computer networks, complex networks, network science, advanced data structures, graph theory, cyber physical systems, wireless networks, cyber security, and next generation internet. Presently, he is a professor in avionics at the Indian Institute of Space Science and Technology, Thiruvananthapuram, after holding several other respectable positions in IIST. Prior to that, he worked as assistant research scientist and lecturer at University of California, San Diego, USA, where his responsibilities included teaching the senior undergraduate and graduate level course on data networks, research on next generation wireless systems, and has also led Systems and Networking Research Group at California Institute for Telecommunications and Information Technology, and has also led the networking group for the NSF-sponsored Homeland Security projects such as Rescue, ResponseSphere, and the Exploratory Research Project, CogNet. Dr. Manoj is a recipient of numerous awards such as the IEEE ICNC 2015 Outstanding Leadership Award, the Teaching Innovator 2016 Award by the Ministry of Human Resource Development for developing multi-track modulator teaching methodology, and Elsevier Ad Hoc Network Journal's top cited article during 2005-2010 Infosys Research Fellowship Award, to name a few. Dr. Manoj is a member of the Association for Computing Machinery, ACM, Conference Activities Board, IEEE Kerala Session, Institution of Engineers and Information Systems for Crisis Response and Management. We welcome you, sir, to the session.
Yeah. Good morning, and thanks for inviting me for the session. I'm glad to be here. This is the first lecture that I'm giving to an audience organized by Kochi Institute of Science and Technology. I heard about Kochi many places as it's one of the very good institutes in Kerala. So let me get into my talk today. Before beginning, I would like to say that this is a virtual event. I'm not able to see your faces. I can only see my slides. Okay. So if you have any questions, you can actually ask me, or you can type in your chat box, and somebody may help read out the questions to me so I can answer, because I do not see the chat box in front of me. Okay. So today we'll be talking about Internet of Things for Industry 4.0, of the very relevant topics, and it is important for the topic of the short-term training program. So let's look at a brief overview of what are the industrial revolutions that we had seen in the past. Okay? So the Industrial Revolution 1.0 was mainly influenced by the invention of steam engines. Okay? There were many engines created, there were many machineries created in the 1700s or late or second half of 17th century, where one of the biggest industry was actually spinning industry or textile industry, where they used to make machines. One of the machine was a spinning jenny, which was a machine for spinning. Uh, Second important thing was steam driven engines that could be used for linear motions that can be used for pumping water or oil. Okay, so the power of steam was identified and used for generating motions, and that is used to get some work done in pumping water or oil. And James Watt was actually a technician who was actually recruited for repairing the machines called Newcomen steam engines. And he found a way to reduce the wastage of steam because of the valves kept open for a long time. Steam was wasted and efficiency was low. And he made his engine patent in 1769. And this is actually one of the original pictures of the James Watt steam engine installed in Spain, now resurrected as a demo piece in a university there. So they actually have the engine here, and that produced through a lever here to make a rotary motion. This rotary motion could be used for various applications like textile spinning, pumping water to run trains, and so on. So that was one of the biggest inventions that enabled the first industrial revolution. uh, Second half of 17th century. Now, 18th century had the fortune of many excellent scientists who actually gave to very innovative products dealing with the electricity. Production of electricity, transmission of electricity, distribution of electricity, as well as applications or devices that can use electricity for various purposes. Of that, the most noted was Michael Faraday, who actually made motor as well as a generator, or the principles of electric motor and generator. And by the later part of the 18th century, many innovators in the US produced effective electricity production, transmission, distribution, and reservoir play. So this is one of the light bulbs which could produce 16 candle strength, light intensity, invented by Thomas Edison in 1879. Nikola Tesla was another pioneer who developed the AC motors and generators as well as distribution mechanisms. So he pioneered one of the earliest hydroelectric power stations in Niagara waterfalls in US in the late 1800s. Okay. So together, the second industrial revolution was driven mainly by the electricity as well as related inventions. Now, that led to many scientists working on how to control the current flow, how to generate electron flow, how to generate electrons through vacuum, and how people can actually use electron flow, passing through cathode, pass between cathode and cathode as well as anode within vacuum tubes. In 1904, John Ambrose Fleming invented what was called the equivalent of vacuum tube diodes. Okay, and he experimented. He was able to control the flow of current in unidirectional manner, and it had many applications as subsequently worked by many other scientists, including Lady Forrest in 1907 devised what was called the vacuum tube triode. So this could actually control the current between the cathode and anode by supplying a signals to a mesh sitting between the cathode and current, and that had many applications, including making amplifiers, making switches, and so on. So, in fact, a lot of applications came into the world by the use of vacuum triodes. People started inventing mechanisms, new mechanisms for triodes and new technologies for realizing triodes. And in 1947, three scientists from AT&T Bell Labs, John Bardeen, William Shockley, and Walter Brattain, developed what was called a point contact transistor, which was actually a non-vacuum tube device that could accomplish the same functions of a vacuum tube triode. So soon, innovation started, and that paved the way of revolution, actually 3.0. This is actually not 2.0, it's 3.0 by electronics and the subsequent innovation of computers as well as the applications based on IT. So collectively, the Industrial Revolution 3.0 has started. It has developed many generations of many G's of computing applications. So first generation computers using vacuum tubes. The best example was a Colossus machine developed by Alan Turing, the famous computing scientist in UK, followed by mid 90s John Mosley and Prosper Eckert developed the first successful electronic computer called the electronic numerical integrator and computer, which had used about 18,000 vacuum tubes, 1,500 electrical relays, 167 square meter space, something like a very big hall, and the machine collectively weighted about 30 tons, consuming 140 kilowatts of electricity. Today, if you look at this power consumption, that is equal to something like an institute's all power consumption. Okay. Now, many developments happened in the computing architecture. Second generation computer happened with the transistors replacing the vacuum tubes, which made the computers very fast as well as cheaper. Software, the industry got developed, new high-level languages like COBOL and Fortran got developed, and leading to the third generation of computing industry that spans between 65 to 18. You can see that the generations have become very short over the years. So, integrated circuits and microprocessors were invented during this period between 1965 and 80. So right now we are in the fourth generation of the computing industry led by the VLSI technology. So we have highly integrated or very large scale integrated microprocessors driving our computers. So parallelly from 1969, 1960s, we started the development of the internet. Okay, so you can see there is an overlap between the third industrial revolutions, later part, as well as the computing industry developments, fourth generation, that actually led to the development of the internet. Okay, now we are in the fourth generation industry revolution that we abbreviate into Industry 4.0. So this is actually marked in 20. So we can see that. So every century led to a rapid or radical change in the technologies that drive the industry. So today, when it comes to Industry 4, the key technology elements that we are going to see changing our lives will be Internet of Things, artificial intelligence, robotics, and cyber physical security. Okay, if you look at the short-term training programs topics, pretty much you will be covering what is relevant for Industry 4.0. So that's very, very timely workshop. So thank the organizers for choosing this. So now let's look at the Internet of Things, which is the key enabler of Industry 4.0. Okay. Now, before we come to the industry of Industry 4.0 as well as Internet of Things, I just want to recollect the some of the important things in the development of the internet, because this internet's if you see internet as a generation, the current generation of internet is actually internet of things. So we'll just recollect a few points of the internet's evolution too. So this is actually the picture taken from the paper written by Paul Barron of Rand Corporation. So he had written an article in 1964 saying the title on distributed communications, introduction to digital or introduction to distributed communications network. So this he had anticipated the centralized network as well as the decentralized network, which was mainly the telecommunication network of the those days. Okay, these networks were having some similar serious problems of uh, lack of robustness when it comes to reliability of communication. So, for example, when you have this particular central node that is actually enabling the connectivity of all the stations together, this node, the central node or hub node, actually faces a serious single point failure question. So, which means that when there's a failure on this device, the whole network actually fails. So even in the case of a decentralized system where you have several such distributed clusters connected together by the trunk lines, this is how most of our telecommunication networks work at one point of time. So even if there is some destruction here, so you can see that the whole nation is into split into three separate regions without having the connectivity across various regions. So that way, there is a serious issue of robustness in the network here. So he anticipated that in the future the network will be a fully distributed network with no single node playing a key role in the operation of the network. For example, if you have one node affected, so this node is affected, the rest of the network doesn't have a problem because only that node is affected. Every other node can communicate with every other node without having any issue. Maybe a slight reconfiguration of the routing paths will be enough to do that. So this was one of the earliest documents where the concept of internet was outlined. This was written as a policy document based on a contract by Defense Advanced Research Project Agency of the United States. Parallelly, 1965 to 1969, Professor Leonardo Kleinrock of MIT developed the theoretical models, MIT and UCLA developed theoretical models for a packet switching framework. Say, instead of having a direct end-to-end path, so the nodes in the network had short bytes of information that will be sent over these lines, which may be buffered in the queues there before getting forwarded to appropriate path. So this switching mechanism was theoretically studied. Delay analysis was actually made, and he actually set out to make the first prototype with a funding from Advanced Research Project Agency, and the network was called ARPANET. This was the shape of the network in 1969. So they had UC Santa Barbara, UCLA, Stanford Research Institute, and Utah University becoming the four nodes, and each of these universities had one of the computers connecting to the network for A-level communication. So between the nodes they had leased lines. This was actually a leased line, and over the lease line they allowed packets of information. So basically the earliest prototype for packet switched network or the earliest predecessor of the internet in the form of ARPANET was formed in 1969. Okay, but very soon people and universities started adopting this network. More and more universities joined the ARPANET, and it became very, very big infrastructure for communication. So this is actually an estimated topology of the internet made by an agency called CAIDA in the year 2000. So here they have represented the regions of the world, countries of the world in as a skitter graph. So where some part of the US is present here. This is actually part of Asia. So you can see Bangkok, Jakarta, Delhi. Delhi is actually here. Kabul is here, and Abu Dhabi. And you can see Seoul, some part of Asia, Tokyo, Seoul, Wellington, New Zealand, Honolulu in US. So this the whole thing is actually the cities in US. Okay. So this was the whole US, and cities were marked with the organization. So this every sport is an organization. Okay, in this graph, and you can see Europe here. Okay, so the rest of that is actually Asia, Australia, and other ones. So they have marked the nodes with the higher traffic between them at the center. So which means the nodes at the center is having higher traffic, and the nodes at the boundary had lower traffic. Okay, this was an estimated network connectivity or organizational connectivity in the year 2000. Okay. Now, in the year 2010, 10 years down the line, the same agency called Cooperative Analysis of Internet, Data and Agency for Internet Data Analysis, they replotted the same topology. Every few years they used to do this, and they found that the network has become so congested, and is a graphical representation of the world's organizations connected over the internet is too complicated. You can see the density of the nodes at the center and the amount of traffic they see, as well as the number of organizations across the world, that actually made the internet a very, very complicated, a very large infrastructure. Okay. Now, when it came to 2013, okay, they have replotted that. Then the internet had two different addressing mechanisms, IPv4 addressing as well as IPv6 addressing. They had two different networks altogether showing, representing the communication between these addresses. So here you can see IPv4 addressing has actually, exhausted its the whole address space of 2 power 32 addresses in this space. Okay, so the number of devices connected to internet has far exceeded this particular number by this year. Okay, so new addressing with the 2 power 128 address spaces have been developed, which will include these 2 power 32 addresses within that, and that was called IP address version 6. Okay, now you can see this is almost like the IPv4 of 2000s. Okay, this is similar because in 2000s, if you see, you might find similar complexities. Okay, so that way the internet has become very, very complicated beyond the way that we can actually describe, represent, understand, and even manage that in a meaningful way. Now, this picture showed the connectivity diagrams between organizations, but this picture is actually showing how a hosts are connected in the internet. Okay, this is like every node here. For example, this particular node, this is actually zoomed from here. If you take this particular node, this is a node with an IP address. Okay, which means this can be a laptop computer or a mobile phone with an internet data connectivity or an IP address, or a computer on your office. Okay, so you can see that every device is having one IP address in this. So this picture is actually developed in 2005. This is again only an estimate, probably a small fraction of the whole network, how the internet infrastructure is actually connected. So basically, what I want to say is that the small network with the 4 nodes have grown into something like a very, very big infrastructure that cannot be easily managed or configured or understood, even represented on a topology diagram. Now, if you see the evolution from the 70s of hundreds of nodes to 20 20 with the 50 billion things. Okay, so originally we considered hosts which are actually computers in the internet, computers connected to internet. Then it became like users because a user may have many computers, so we have reduced number of computers. Now what people think about is about things. Okay, now what is the meaning of this thing? And why is it relevant for us today and maybe in the future? And people expect various numbers like 20 billion to 50 billion by 2020, and even people anticipate that 1 trillion things will be connected to the internet by 2025. So we do not know how exactly these predictions are, but one thing is very sure that a large number of devices that are non-traditional things. Okay, these are actually non-traditional computing devices. Computing devices that are therefore called things. Okay, so now what that means is these devices are actually devices which are not called like the desktop computer, laptop computer, or even your mobile computer or whatever. So now what I have mentioned is, so by 2025, even though we have only 7 billion people, with less than half of the people are connected to the internet, even some of the services have several billion people, but the number of devices that are going to be connected is going to be very, very high into trillions of things. And these devices are going to be connected in a very unplanned manner, which might have a serious impact on our lives. So when it comes to IoT, as I mentioned earlier, these are things which means that even your gate can be considered as an IP addressed device in the internet, or even you may have some kind of a representative address like an IP address for your side yard. So you may be able to send some resources to the side yard, some instruction to the side yard, or some sensed data from the side yard or backyard or front yard. So that these are all examples of the things here. So streets may have certain ID. Even street lights, electrical subsystems, plumbing works, signal lights, all these are actually part of the system. Even non-traditional computers like tables which are like wooden furnitures, pens, books, stationery items, all these are actually examples of things that will make networks within how, and the or every room you will have several such things making dozens of systems, and every house is considered as a large system of systems. So that way an IoT system is nothing but a system of large number of systems. Okay, now some of the examples, very recent example, we have thousands of examples, but I only collected a few number. This is actually a pen enabled for IoT operation. Okay, this can be a normal pen, but it can also record what you are writing, or it can also interact with the computer to record what you are writing, and so on. There are so many features that allowed by this. So this is an address to communicate with the internet. So this is there are different companies are producing. I just got only a few examples. So this is actually a plug that can actually usually deliver power to your electrical appliances, and this is actually controlled by Amazon, Alexa, Google Home, or Nest, or whatever kind of controllers that can be available to work with it. So you may be able to control the current flow, measure the current flow, and take a predefined time to turn on the power, even to control the voltage that is to be supplied through the device, okay, in an advanced way. So you have several such plugs available, IoT enabled plugs or sockets available in the market. In fact, if you here down the line, you will have almost all ordinary plugs will have some sort of an IoT connectivity. Now, This is an IoT-enabled bulb. As you see, dozens of manufacturers come with IoT-enabled bulb. This has several purposes. It can actually use as a normal light, or it can work as a mood light. Mood light is actually a light that can change its color, tint, hue, everything depending upon your mood and so on. So it can operate using the internet or using any of the home controllers that you have at your home, like Amazon Alexa or Google Home, even Siri kind of devices. So this switch that is shown here is actually an IoT-enabled switch. Actually, you don't need to press the switch to make it work. You can speak to the switch to make it work, or you can send a message from your mobile phone to make the switch work, or even just to speak to your home surroundings, and the switch will be effective in its purpose. The speakers. This is actually a speaker. In fact, almost all multi-billion dollar companies in the IT sector have IoT devices starting with a speaker. Uh, Google, Amazon, Apple are all examples for that. Now, I just want to highlight a few options. In fact, out of the dozens of options in the sports segment, I have mentioned only two categories, athletic and gymnastics. Okay, so you can see, the sports activities such as running, jumping, and throwing, or gymnastic activities such as aerobics and dance sports or yoga. We have different IoT devices available to help you carry out your operation. Okay, so you will be able to measure information like speed, length, distance, calories, heart frequency, altitude, foot contact, foot landing, cadence, steps, hydration, everything that will be monitored and will be available for the effective coaching by the authorities or administrators. Now, even for example, this is enabled by IoT-enabled things like watches, wristband, shirt, socks, shoes, so on. All these were traditional things, but today they are all enabled for IoT operation, and the whole new invention is coming. So this is why it's very important to have this kind of events, because everything invented. Okay, I'll write here everything invented in 18 or maybe 1700 to 2000, okay, is reinvented now with the IoT enabling. In fact, this particular plug was actually invented in the 1800s, right? And the pen was invented by even before that. But everything invented in the last 300 years are getting reinvented. And this is the biggest opportunity for all the students as well as faculty members attending this. So as I mentioned earlier, these things, what was once used as a normal shirt or normal mat or normal skipping rope, are all getting reinvented with the ability to communicate with the internet. So that's why this is becoming very, very important. So if we take one representative picture from this company called Libelium. Libelium is a company that produces sensors, actuators, and control software, as well as some of the hardwares for this smart city applications. Okay, send wireless sensor devices and so on. So they have applications ranging in every spectrum of our life. Okay, so starting from shipment, monitoring vibrations, stocks, container openings, cold chain management, and insurance purposes, to infrastructure monitoring. This is actually structural health management of buildings or bridges or whatever. So you will have IoT-enabled bridges, which means a very important segment in that the bridge can be monitored, assessed, and detected for any potential fault or diagnosed for any possible future issues. So then environment. offers an innumerable number of opportunities, including water quality and uh, uh, this forest fire detection, air pollution detection, and smart animal husbandry and physical activities, measurements, and so on. So then comes the smart city related things where there is smart parking system, smart waste management, then smart industry monitoring system, industry actuator control systems, and perimeter access control for the security related aspect, and coming to the for automobile transportation sector where signaling, traffic alert system, to residential situations where you will be able to do shopping, lighting, and whatever city related management required. So that way every segment of our life is actually reshaped by this industry 4.0. One of the examples is an example slightly old, like 2-3 years old. In an IoT world, 2-3 years is like a generation. Okay, so this is actually appeared in the Forbes magazine. So a shopper is actually entering into the Walmart like a smart shop. Okay, so as soon as she entered, she is identified, okay, because there are identity information available through the smart clothing that she wears. So the scanners will identify the tags on her clothing, and she is identified as she walks through. This is one, and as she walk through the aisles, the items stored in the aisles will give her necessary information for what they are, how they can be useful, and so on. So that way they will give necessary information right there. You may even speak to it. The shelves may speak, or the product itself may speak to you in response. And when you take some item into your basket, so the reader will actually identify what item is taken. The cart will identify what item is actually loaded. Even it can actually be billed automatically. So it may also alert the shop owner saying that the item is actually moved. So some replenishing of the stock will be required. So in fact, it is not even necessary to pay in today's world, but still, when it comes to paying, the automatically the credit card will communicate. Today you have the near field communication technology, which only needs to be near the point of payment device for a credit card, so that the payment process can be completed. So you just walk into the shop, take the necessary things, just walk out, so your transactions are actually done. So this is actually one of the examples. But the biggest and most happening place is actually smart home. Okay, in addition to the smart city, where one of the important component of the smart city is actually smart home. Okay, let's spend a few minutes of time here. As I explained here, this picture tells a lot of stories. Actually, in fact, a lot of inventions can be imagined and made just with this picture in place. Okay, let's look at this particular room. Okay, this is actually a room called bedroom. Okay, so so this room is actually a virtual reality room where you can actually have what is it called, the ambience loaded to the room. Okay, the ambience that you like. So this may have a Saharan ambience, whether the room will actually have the lights and images and sounds of the ambience of Sahara, or even it can have the Niagara fall like ambience. So it may have a rural ambience or an urban ambience. So the room will actually load what is called an ambience that will suit your mood and it will. So the room will also have some sort of an identity or some sort of an instance or even an operating system that will be able to do that. So you will develop a lot of applications for this particular space. You may develop a profile for the room that will be available over the internet for others to download and use it and load. So you will be able to take money out of that business, room profiles or your applications. So that's about the room segment card. So this itself is a market segment for various products and services. Now come here. This is actually the traditional bathroom. So when it comes to traditional bathroom, we have plumbing and other resources for taking bath. But in the IoT enabled world, this will do the purpose of a biomedical lab. Okay, so what that means is as soon as you step in and wash yourself and come out, the bathroom had actually conducted a lot of biomedical experiments or biomedical tests on you and actually obtained your health related status. It may prognose whether you are going to get a problem in the near future, or it may even create an appointment with a doctor based on your health conditions or anticipated health conditions. So it's possible even in today's preliminary or rudimentary technologies. As soon as you step into your room, your body mass index can be measured, and it can, based on the trend of the body mass index, they can actually give you alerts for your health status about what precautions you have to take. And so this room actually is going to be another another medical market segment. Okay? Even in a simple way, many people have waiting machines and so on in bathrooms too these days, but they are all not enabled for internet. If it is enabled for the internet, that will make a different situation. Okay, now comes the let's look at this garage. Okay, this garage where the car is stored during its resting time or night time, so will actually work as a workshop. Okay? So garage or workshop will conduct a lot of diagnostic tests when you are actually resting in your bedroom. The car is actually undergoing a health checkup. Okay, now these days most of the cars are actually getting health checked through computers. They will run a diagnostic procedure. They will take hours to do that. Sometimes a full diagnostic test can take like 6 hours. And at the end of the diagnostic section, they will see everything is fine or not. If it's not fine, it can actually book an appointment with the workshop for replacement. So it not only updates software for the car, because software update may be required very frequently for cars in the near future. Okay, then it charges the car for the electric power. It does diagnostics for the car, and it can even do what is it called uh, yeah other software updates I have mentioned. So that way it will be able to do a full diagnostics of the car, which might avoid frequent visits to the workshop, or which might have a better planning for car maintenance related activities. So that way, if you look at every segment of your house will be different market getting created. Okay, now the last thing, we don't want to discuss everything, but a few points. This is actually the kitchen where you will see a revolution in robotics. Okay, so we can say here many of the traditional devices that are used for cooking will be replaced by a robotic cooking plant. Okay, what do you mean by robotic cooking plant? This is not I said plant, because today's kitchen is what you have some area to work. You have a cooking range or a stove, or have a refrigerator sitting elsewhere, and you play a major role in bringing these ingredients together, washing, cutting, arranging, and then cooking as well as serving. So the whole layout of the kitchen itself can change. In fact, your kitchen layout will become something like a streamlined factory plant, where you have a place to have arrange the raw materials. Okay, what do you mean by raw material? You have vegetables and pulses and milk in predefined cartridges, and with some pre-processing done, you will load these things. Okay, so these loaded cartridges of raw materials will be processed by robotic arms. Okay, So robotics arms, and it will actually undergo different programs to do different processing sequences, and then it will be taken through a cooking region. This is where the heat is applied and the food is cooked, and you will actually be getting the processed food here. Okay, to program the food processing system, and the whole sequence of processing will be carried out, and food will be delivered here. The whole layout of a kitchen that we see today will be completely revised, reformatted, and you will see that very, very big market segment will be developed by this particular kitchen. So this is where the applications of IoTs are going to be far uh, uh, advanced than we can actually imagine in 2020. So there are many sectors. The most leading sector for IoT is actually smart cities, then health, then smart energy, as well as security. Then the key market drivers for IoT is because of the pervasive computing solutions, as well as availability of smartphones to allow pervasive communication, and even for the need for reducing costs. Reducing cost is possible because of the large volume of data available for analysis, data available for diagnosis, as well as reducing the maintenance costs. Now, the difficulty of IoT segments or the market inhibitions, which means the challenges faced with the market, is mainly because of the profitability of the solutions, as well as the heterogeneity of devices. So in this space, heterogeneity is actually going to be going away in the near future because of the major players are actually into this. All major players are in this market segment. So you will see a technology consolidation in IoT segment by having certain standardized hardware components and software platforms. So that will actually reduce this heterogeneity issue. Then the potential use for IoT customers, or influencing factors for IoT customers, is actually flexibility as well as security for customers. So now let's look at a few points about what is IoT architecture. Okay, so here I will not cover all the architectures, even though there are several standardized architectures from IBM, Cisco, Oracle, Google, Facebook, and Amazon also have their own proprietary products with their architecture, but they do not reveal that. IEEE has also come up with an IEEE P2413 standard architecture, but I will just mention a popular, a three-way representative architecture for this particular pattern. So this is a very, very important and open research area. Those who are looking for architectures development or new architectures handling and so on. So the three-layer architecture for IoT is actually shown here. The lowest layer is called the perception layer. This is here, and it is identification of the objects as well as gathering information. The responsibility is to perceive the ambience, gather the information. So this is sometimes called the sensing layer in some of the literature. So this is where the sensors are. And second, the network layer. So this is the entire internet uh, uh, layer. We can say internet layer, or the internet communication infrastructure is represented in one layer. So in fact, this is split into several layers, as I'm going to show you in the subsequent slides. Then comes the application layer. So the application layer, depending on the type of IoT as well as industry technology application, you have various purposes. Now here, the network layer, as I have mentioned in the last slide, will be not just a single layer. The entire internet protocol stack is actually captured in this one. Okay, internet protocol stack has 5 layers. I have shown here 4 layer. The physical layer, which is actual communication layer. Data link layer is where medium access control protocol is executed. So then comes the routing layer or the network layer. Above that, you have the end-to-end transport layer, either running TCP or UDP. or now the Google developed protocol called the QUIC protocol. Okay, so in the network layer, you have either IPv4 addressed system or IPv6 address system, but there is only IP that is valid in the network layer. So this entire internet protocol stack is actually captured in the network layer of the three-layer IoT architecture. Now, but the point that I want to suggest is the three-layer architecture suggested popularly in the literature, as I have shown here, perception network layer architecture has some serious shortcomings. One of the important shortcoming is actually on the lower layer, where the perception is not the only activity that the network is going to do. So that's why it's modified with a different layer at the bottom called cyber physical interface layer. Okay, so the difference between the perception layer and cyber physical interface layer is because it consists of one, the sensing infrastructure, second, the actuation infrastructure, okay, and third, a cyber physical interaction layer too. So there are three important aspects that will be included in this cyber physical interface layer, that is sensing, actuation, and cyber physical interaction layer. So whereas the other layers like the application layer might have a significant artificial intelligence capability added, uh, and the internet layer does not have any change. So that way, this three-layer representation is much more accurate for today's IoT layered architecture than what was earlier discussed in the three-layer architecture. So again, this internet layer is expanded to have the entire internet protocol stack having multiple separate layers. Now, example of the protocols, as you see, when you use the internet layer, you may use the Wi-Fi protocol for the data link layer as well as the physical layer, IPv4, IPv6 for the network layer, or TCP, UDP, QUIC for the transport layer. So you may have several application layers like HTTP, DNS, and various other web-based artificial intelligence services, machine learning applications, or big data analysis applications, or whatever required for uh, the effective machine intelligence or AI layer at the application layer. Just give me 1 second. Just hold on a minute. So, yeah. Now, as I mentioned earlier, today's IoT applications are not just the things, okay, not just the things in the sense that not just the non-traditional things that are becoming significant, okay. The cyber physical interface layer is becoming more meaningful and significant as you see, it's beyond the sensing actuation infrastructure, but it's actually an infrastructure with a cyber physical interaction layer. Okay, so this is why new generation applications of IoT focuses on robotic robotic things for industrial IoT. So this is where this particular workshop has a significant interest, where you have what is it called robotic things. So this is where Industry 4.0 is actually significantly enabled. Okay, now for that, and this is a layer-wise architecture for Industry 4.0. So here you have the application layer at the top, which allows various marketplace application programming interfaces. So this is an application, this is application, various range of applications and there are services that are provided to users based on this application layer. And in fact, several business processes will be interacting with the application layer to derive, data analysis results and translate the information into money. Then this application APIs will interact with the IoT platforms landscape, okay, through interfaces such as learning and contact services or models actuation interfaces. So if you look at this actuation platform details or IoT platform details, so there's a service layer which is dealing with the data analytics, data management, and various data abstraction services as well as data access services. Okay, so there are two factors in this. One is that getting the intelligence of information by using proper analytics. And second thing is orchestration. So orchestration is actually bringing together various modules to accomplish a larger task. So for example, to get a food cooked, you need to have various modules working in sequence. Okay, you may have to have the food processing, food processing, raw food, and what is it called? The raw food handling unit that should actually be working for a certain amount of time. After that, the food chopping devices as well as cutting device and cleaning devices should be working for a certain amount of time. Then it should be actually moved to what is it called, the cooking region, and then the serving region. So that way you can see a series of devices should work in consolidation sequence in a coordinated manner. That is it called orchestration of resources within an IoT landscape. Okay. Now, below this abstraction layer, if you look at it, there is a physical layer. So they call that devices and controllers. And in this, you can also see here. I do not know if you see here. I have this menu. Yeah, okay. You can see robotic things in addition to the traditional things. What are the traditional things? You have the communication devices and simple activation devices like lights, switches, doors, windows, fans, and so on. Small appliances, devices, and so on. So in addition to that, whatever things that are called robotic things with ROS or other operating systems can also be forming the physical layer to it. And then comes the communication infrastructure. That will be what I call the internet layer or network layer. Okay, that is provided. The service of the network layer is provided by a gateway device, and then it will be going to a small cloud called the edge cloud, which will be providing access and some of the computing services to these things. Okay, then it might be going to the real internet-based cloud, which will have much higher capacity. So that way, this Internet of Robotic Things will additionally add the robotic things that will enable a lot of additional services, lot of actuation tasks, lot of orchestration requirements to the Internet of things, Internet of Robotic Things. So if you see an architecture of Internet of robotic things, so this is a conceptual architecture of the robotics. This is when it comes to architecture, this is almost synonymous to the computer architecture, where a computing CPU interworks with several of the units such as memory, interface devices through a bus. Okay, through a main bus or auxiliary buses or whatever interface devices available. So that way, this particular thing, IoT, IoRT, Internet of Robotic Things, event bus allows communication between the platform as well as robotic things. If you can see that the robotic things can be or the sensor or the cyber physical interface layer can have robotic actuation involved or static actuation involved. When it comes to robotic actuation, you have things that are moving, things that are making action, which should be very, very critical and very carefully handled. Whereas the static actuation might be involving like turning on switches or turning on some of the devices. Okay. So in addition to this robotic actuator as well as static actuator, there are other variety of actuators that might have been playing a role. So all this communication will happen through the event bus, where the actuator and executor component will instruct the appropriate actuators to take decisions. Okay, so as I mentioned earlier, the orchestrator requires a task execution planner. This task execution planner will decide what kind of a series of tasks will be required to accomplish a task in the overall system, and this accomplishment might require a series of minor things to work in a coordinated manner. Now there will be service level contracts or agreements. So these contracts will be between the users or the business community and the IoT platform that you deploy. So this will ensure that the data requested or the quality of service requested will be guaranteed, and they will be able to implement some of the policies, some of the security requirements, some of the conditions of their agreement. So this will ensure accountability of the usage of the platform. So as I mentioned earlier, this is almost like a computer architecture extended to an IoT system where there will be large number of devices controlled by the as a control system. Now one another thing that I want to mention in this context is the operating systems. Earlier, I have mentioned that uh, the central system will have a large number of things. Now, individual devices should have their own operating system. So, what I mean to say is that so each one of these individual devices are nothing but embedded computers. Okay, so these embedded computers might require an operating system to make it as a working computer. Okay, that may have an address like an IP address. It may have protocol implemented for communications. It will have sensors available for sensing some of that. It may even have actuators connected to it, so the embedded computer can actually send the actuation messages. So basically, you still need certain important system softwares within the device. So what I mean to say is that each one of these actuation executors might require this operating system. So just some examples of the existing and popular operating systems are here, which are highly specialized for IoT devices. So one is actually Tiny OS, Quantity OS, Light OS, Open Wireless Sensor Network, SOS, RIoT, and so on. So even embedded Linux is actually a good choice for such operating systems because Raspberry Pi, popular computers can actually use embedded Linux. Raspberry is one example of a variation of Linux. Now, some of the IoT hardwares are so simple that they do not have any operating system. Okay, they don't have any operating system. So what that is an example, as an example that we can discuss is the Arduino boards. Okay, Arduino boards do not have even OS, but it will have only a loop-based program. So because they are to be so simple that the operating system can be very expensive or very complicated. Okay, so they usually have a bootloader and loads a run a user program, and this user program will do what you need within the loop. Okay, usually within the loop that you run will have gathering of input data, processing the data, and get the results and even act on the results by sending appropriate signals to the output ports. So this is what usually will be done in one particular thing. So if you look at one example, say this is actually a sketch. Sketch is a program for Arduino. So you have two parts. One is a setup part. So this setup part will have what is called initialization requirements, variable definitions, input-output declarations, output port, input port declarations, output port declarations, serial port initialization, library inclusions, and any other installation that you need for your second part of the program, which is nothing but a loop. Okay, so all the what is required here should be initialized in this part. So what do you do typically here, as I mentioned here, receiving the input, processing as per your IoT requirements, producing the output, and transmit the output. Sometimes you will send it. Now, many cases this is running on one time, once loop, and it will exit. But usually, what people do is to continue the loop forever, because you may need it. So, for example, just look at this. This is a simple program for unlock read serial port. So the serial input pin on pin 0 will be read, and the data will be used. So here you can see that initialization part is here. Uh, you can see the setup. You only initialize the serial port with this 9600 bits per second speed. And within the loop, this is a loop where the user program is doing some functions. So it actually reads the analog pin A0 and stores the data into sensor value and displays that. And then after 1 second delay, it reads it again. So it basically senses some of the data available through a particular port and just puts it. Now, this is another example where you are actually, using a potentiometer like a circuit using a device. Potentiometer is actually a meter that is equivalent to, what is it called, a variable resistor. Okay. So here you can see this particular program. You define the initialization part here. Oh, I think there is some echo, the long delayed echo here. So maybe you can see the installation part. The analog pin is enabled as A0 pin. Then an LED output pin is actually defined on 30th pin. Then a threshold value for checking a if condition is also set. And then the within the setup point, you will actually make the LED pin defined as an output port pin. Okay, serial port is enabled with the 9600 bits per second speed. Now, within this actual program, what you do is you read. This is a loop function beginning here, and you read the analog pin. Analog pin is actually defined here. A0. This A0 pin is read, where you read the analog voltage there, and you check if the analog value is greater than a threshold. Then a high signal is sent to the LED pin, which is actually connected to an LED, and the LED will be glowing. So if the analog value measured through A0 pin is higher, then an LED is turned on. Okay, maybe you can drive this LED pin through a relay, electric, electromechanic or electric relay, that will be able to drive a light or something. So, okay. Now, if its value is less than the threshold, then low signal is actually sent. So, based on what is the value of the analog signal, where a potentiometer is connected, you can actually set a lamp, light on, or whatever control you can do. Then you print the analog value and wait for 1 second loop here, and then repeat again. So this is actually roughly the operating system for this loop serves as operating system for the whole IoT device thing. So this is a slightly different example where you have a large number of pins are used to output with an input signal. Okay, so the for example, you have about pin 2 to 7, 2 to 6, okay, will be enabled as output pin, okay, and the serial port is also enabled with the 9600 bits per second. And you are actually defining the operating system for the simplest IoT device here, okay. So what you do is you will read the serial port, and the serial port gives some byte information, okay, that through the serial port you receive. And then you do what is the information within the variable in byte. So if you send A, then the pin 2 will be high. Okay, pin 2 will be set to high. If you send B, pin 3 will be set to high. If you put C, pin 4 will be set to high. So depending on that, depending on what is the signal that you communicate to the board through the serial port, you might turn on say, light 1 or light 2, or then the fan, or the TV or whatever. So if you see, say you will be able to take a action, different actions for enabling different systems within the house or within the smart system that you are building. And then you will continue this loop to do various actions. If it's only one time action, you can make changes here to do only one time. If it needs to be refreshed very quickly, then that also you can do. So whatever you write here in this OS like thing, that will be implemented too. So this is actually a simple code for running an HTTP client using Arduino like board. Okay, as I mentioned earlier, this needs two header files, a bridge header file as well as a HTTP client header file. And the setup of code is here. So this entire thing is a setup code. So you will have the output pin 13 defined, as well as the bridge library is initialized. And then this is actually a symbol. You just use this as a technique to see whether the bridge library initialization is complete or not. Okay, so which means the signal on the pin 13 is actually low when the initialization is beginning. And after the signal is, after the initialization is completed, the LED is turned high again. So you will be able to get an indication that the library is enabled. So you will be able to run the rest of that. So then serial port is initialized. So now within the program, this is actually the operating system part or the code part. So you will be instantiating a client from the HTTP client library. So you will be able to have this client communicating to an external website by calling client.get. You must be remembering, if you know HTTP, get, put, OK are messages or commands used in HTTP post to communicate between the client and a server for various interactions. Get will actually download a content by visiting this particular website, arduino.cc, and this text file, ASCII logo.txt, will be downloaded to this particular Arduino device or sensor. So basically, the sensor here, the IoT device, is actually a web client enabled device. Okay, so then it will read the data from the client and print the data so the user can see in a computer. Every 5 seconds, this will be keep repeating. So you will be able to see what is the data that is getting updated in a website. Say, for example, if the website is showing daily temperature, and this device will visit the website showing daily temperature and download the temperature and actually display it for you in a way that you can see. So this will be, if it's a clock, internet-enabled clock device, then it will be able to download data from a website every 5 seconds and update the time in front of you. Or if it's a stock market ticker, the ticker will actually download what is it called as stock price changes of a particular listed company, and then you will be able to get it shown in that. So you can even take a decision. When you get the stock market thing, so with the prices going high, you can take a decision. Okay, you can actually send a message. Okay, buy or sell or other kind of decisions. Okay, the temperature is very high and the temperature is available from a server, then you can take an action to turn off certain equipments so that the heat can be reduced. So that way, a lot of implementations can be done. So this is an example of operating system that are very simple, very lightweight, and you basically have everything defined into just one particular function. But more complicated systems will not be easy with that kind of a simple operating system. So that's why let's discuss a few design issues. Now only a few minutes before we can stop. I'll briefly touch upon the design issues for IoT operating systems, the available time. Okay. Now, so the design issues of IoT operating systems are here. One is process management and scheduling, memory management, the model used for developing the kernel, energy efficiency requirements, application program interface, code upgrading as well as reprogramming. It's very, very important thing for various things, even for many robotic devices and so on. The footprint requirement, real-time functional guarantee, as well as reliability. So let's very quickly go through each one of these so that we'll be able to cover everything in brief. Okay. So in traditional operating systems like Linux, Windows, and other operating systems, we have one stack memory for each process. Okay, we have one stack is actually memory area that works in the principle of last in, first out. Okay, LIFO. Now, which means this is very important for the process scheduling, process switching, and so on. So, not only that, the traditional OSs, the process management and scheduling, the process is complicated. And each process maintains data and information in its own memory space. As a result, switching between processes to be done rapidly. Okay, this switching rapid requires several data copying and context switching. Okay, so between processes. So these are actually very, very expensive in terms of energy resources. Okay, one of the important design requirement for the entire IoT world is energy efficiency. So as a result, when you have the processor running process P1 for one time, and it has to save its process state and load the processor P2, then in order to load the process P2, you need to restore the state of the second process, and you continue to run the process P2 before switching to P1 again. So while you shift to P1, so you need to save the process P2 state again. So you need to have a lot of memory copying required when you use one stack for each process. Okay, so that way the process switching requires a lot of memory copying that has to be avoided. So IoT operating systems should efficiently handle resource management mechanism to allocate CPU time, shared resources, and APIs. Now, second thing, as I mentioned earlier, memory management. Usually in traditional operating systems, the memory is often allocated exclusively for each process or task. Okay, it's good for security. It's also good for task management. But IoT devices have small resources, including small amount of memory. So that way, this limited memory has to be allocated, and you have to ensure fairness among the processes too. So that way, shared memory allocation is preferred in order to reduce memory related expenses in terms of energy for IoT operating system. And the third important factor is the choice of kernel. Okay, you can have either a monolithic kernel or a microkernel architecture for the operating system used for IoT operation. One of the in fact, different makers make different kernels for their implementation. So, usually the monolithic kernel has the approach where the entire OS is part of the kernel. Okay, that's very big in size. Mostly a single large process handles the service of the kernel, and the coding implementations are easier. Reliability and security are to be careful because since it's a big unit, monolithic thing, if one module fails, everything will be affected. The other approach is microkernel approach, where the kernel's responsibilities are broken down to multiple parts. Only the most essential part is implemented in the kernel, such as inter-process communication, memory management, and so on. All of the responsibilities are implemented as services with separate memory addresses. And the advantage of microkernel is the size is small, but complicated coding is required to implement it. Security and reliability is better in microkernel because many other services are not part of the kernel. It's outside the kernel as a separate service. If there is a security problem, only that service will be affected. So roughly, this is a pictorial representation of monolithic and micro kernel approaches. So this is a monolithic kernel OS, and this is a micro kernel approach. So this is how the separation is. Okay. Now, as you see, in monolithic kernel, the responsibilities of the operating system, such as file system management, inter-process communication, I/O and device management, as well as fundamental process management, will be part of the kernel, where the applications as well as libraries will use the services of the kernel. And this kernel will share the resources of the hardware for various applications. In comparison, in a microkernel architecture, so all the usually attributed services of kernel, such as file systems, process server, pager, drivers, all will be running as separate services at the user space. So, as part of the kernel, you will have what is it called IPC and memory management. Okay, that way, any one of these services failing, that is not going to affect the kernel operations, and the kernel is very small in size too. So, on top of this services, you will have libraries and applications working on. So, this is actually the preferred approach for operating system design for IoT OSs. Even though many people have tried and effectively, successfully arrived at a monolithic kernel of mechanisms. Okay. Now, preference is to have a microkernel approach with an event-driven finite state machine-based implementation, because event-driven model is very good for IoT because most of the activities are in response to certain events within IoT domain. For example, receiving a packet, you may want to respond by transmitting a packet, or detecting an events of risk, events of interest like temperature exceeding, or user turning on, a person appearing in a door, or a person getting into a bathroom or whatever. So you may want to take certain action based on this event detected, or take an alarm about an event detected, and so on. So that way, an operating system which is FSM based, event driven, and kernel based or kernel microkernel based will be very good. Now, as I mentioned, energy efficiency is one of the key design aspects because IoT nodes have energy limitations. So, as a result, the IoT operating system should work at power management as well as energy efficiency. Minimize the memory move operations to a bare minimum, minimize the context switches between the processors, and energy efficient programming should be used. And what that means is you may want to avoid unnecessary instructions to be included within the executable code. Even if the process is not used, it can be kept idle or sleep because that might take energy if it is running idle. Okay. Now, it may have a mechanism to keep a process to sleep, or a wake-up process that will actually bring up the hardware or software to life. Now, application program interface designed for the IoT operating systems should also be worrying about the energy efficiency as well as IoT specificities, where the API should be modular and general for their applications. And it should allow applications to access. Okay, this is very, very important because you have the OS here, you have the applications here for the IoT, and you have the hardware resources, and you may even have the sensors and other modules. So what it says is that the operating system should allow the application to use the direct interaction with the hardware, so you will have better application programs written. Okay, so that way it will have access to hardware resources, sensors, ports, memory, etc., which is directly accessible and even controllable, addressable by the application programs. So, uh, because this is in comparison to the traditional approach where hardware abstraction layers are used, they can create certain performance issues when it comes to these small devices. So, APIs should be simple and minimized. Preferably, asynchronous APIs are preferred to improve energy efficiency. Asynchronous APIs are APIs that do not hold the resources in order to get a response for an request. Okay, so instead, asynchronous APIs will make a request, and when a response is ready, the response is received, and it will not hold the resources, or it will not wait between the request and the response. It will do something else that it has available to. As this is the third important point. First is IPS should be minimum and simplified. Second is asynchronous APIs. Third is it should allow direct access to hardware. Now, as I mentioned earlier, it's very important to upgrade the IoT devices and reprogram the IoT devices. So the OSs should allow upgrading or adding new modules and so on because of the security requirements. So once this device is installed, the device may be deployed in the field. Very, very large number of devices may be present, and the field is inaccessible too. So you have a very low data rate link that will be available to communicate with the device. So you need to have a mechanism that an upgradable operating system over the air, over low data rate wireless links should be enabled for the operating system. That's a very, very important security requirement. So now comes the memory footprint. Most IoT devices have very, very limited memory. And so the operating system should strive to get a very, very small memory footprint. For example, the TinyOS, which is one of the operating systems for wireless sensor as well as IoT devices, has a base version, base operating system, which is only 1 kilobyte in size. Whereas applications can be having more complicated activities to be carried out, so they can have there exist applications that are as big as 64 kilobyte. Okay, even if you imagine an application of 64 kilobyte, you should be surprised because you have tens of megabytes or hundreds of megabytes applications for your mobile phones and laptop computers. So this is about TinyOS. If you look at the Contiki operating system, which has about 10 kilobyte consumption of RAM, and without GUI, and with the GUI 30 kilobytes, and it takes about 30 kilobyte of ROM. So you can see the footprint is very, very important for operating systems for IoT. So what are the basic techniques for generating small footprint? One is microkernel model. Second, modular approach for services. Third, optimization across the whole program sequence. Okay, you can run compiler to optimize the programs across a whole set of programs. So that means we can do what is called cross. We can say 3A and 3B, which will do cross component optimizations that will be faster. Even 3C, where entire call path can be optimized, so to reduce skipping. So you can see that with optimization, without optimization, TinyOS has been able to make significant improvements. For example, so this uh, uh, habitat monitoring application. Okay, habitat monitoring application is actually monitoring the animal habitat by sensing some of the parameters. Okay, environmental sampling. So without optimizing, they get about 11 kilobytes of memory. Sorry, with optimizing 11 kilobytes, and without optimizing, it's about 19 kilobytes. So about 40% saving is actually done. So if you look at this simple application where unoptimized application takes about 1.7 kilobytes, it's about 0.6 kilobytes size. So that way, if you look at the largest application, optimized is something like 63, 60, something like less than 64 kilobytes. This is actually a database which is similar to SQL for operating on this tiny OS operation. So let me just as the time is up. So other important points is to ensure real-time guarantee, because industrial applications may use the IoT for robotics and other process control applications. So you need to ensure real-time support for operating systems. Packets delivery should be on a timely basis. Actuators should be controlled in a real-time way. So that way, you may have to ensure real-time traffic or real-time process support, and reliability as well as security should be enabled too. They should be you know, uh, allowing reliability upgrades or security upgrades for hardware, OS, as well as other elements. So it's very important to have the security not to be treated as a single entity. All the elements, including hardware security, operating system security, application, as well as communication security, should go together to ensure the security element. So let's say these are the summary of the operating OS design issues, or summary of design issues for operating IoT operating systems. So let me conclude here. If you have any questions, I'll take a question. So what we have discussed is uh, um, IoT evolution of the network. Okay, then layers, then OS design issues. Examples of IoT applications. Okay. So if you have any questions, you can ask me now, or put in the chat box. So
Thank you so much, Manoj sir. So we'll share the screen now, which contains the questions which we had taken from the chat box.
okay. So let me just take a look at that. Okay.
So are you able to see our screen now?
Yeah, I'm able to see a Microsoft Word document there for session 2. Yes, yes. Yeah, okay, good question. Could you please explain what sort of technology is being used in mood light? As if I'm not mistaking, you have said its color changes in the customer mode. So by using which IoT technology this mood is being measured? Okay, very good question. Yeah, so I have, you can just look at, you can see if my ambience light is changing or not. Okay, now it is somewhat glowing yellow and slightly bluish now. Small changes are happening in my surroundings now when I do this. Okay, so the light is light that is shown here now on my face is actually changing in its color. Okay, the technology for identifying the mood is actually not very popularly available, because it's a very complicated thing to measure the mood. But the light that suits various modes is easily to observe, and they have, most of the mood lights have different modes defined as happy, sad, and uh, you know, other kind of moods defined, for which a soothing color is actually made. And how this color is made is combination of RGB, red, green, blue lights, which are LED lights that in various intensities are turned on to produce various light combinations. It's very, very easy to make a mood color because these days we have LED lights available. We can very easily program that using our embedded boards to do that. Now, uh, how to sense a mood is a very complicated decision-making process which requires artificial intelligence, uh, may require various of your communications. Okay. One example that I can show is I sent a message, okay. I just typed a message called okay. This okay maybe, or this okay may be reflecting like a very negative mood too. Okay. Now, how this okay reflects my mood depends on what question was asked to me before in my messaging platform. Say, for example, I'm getting a message that you have been given an appointment. I said okay, which means that's a positive. The okay now is reflecting a positive attitude. Maybe I'm happy because of that. Okay, because you got an appointment. The other message could be like, I have noticed that you did not come on time today in office. Okay, the person is sending a message saying that I did not go to office on time, and I said okay. So this okay need not be very happy okay. This can have a mixed okay. If somebody says, oh, you have been thrown out of a position, I said, okay, this okay means I am probably in a very difficult situation. Okay. So that way you need to have very complicated artificial intelligence techniques to measure the ambient information surrounding a person, his communications, his interactions, his facial expressions, to actually measure the mood of a person. And it's not really beyond the ability of today's technology. Today's technologies can actually measure facial expressions and see if a person is really happy or not, even if he is not showing the happiness on his face. That's possible. But the actual realization of how the color changes is because of the combination of RGB LEDs applied with the different intensities. Second, what is the difference between Industry 4.0 and lean manufacturing? Okay. So, in fact, if you see, lean manufacturing is a subset of Industry 4.0. So, Industry 4.0 is actually larger aspect. One is smart manufacturing, remote diagnostics, lean manufacturing. What you call, each, when you order an item that is produced with a very, very low cost. So all these are possible. Even in fact, I just read an article recently saying that in a large textile corporation, where about 5,000 people are working under a particular person. He made the factory a smart factory, and he has been able to prognose what kind of problems are going to be created by which employee next day, or what kind of a fault is going to be caused by which employee's action tomorrow. Okay, if you know that, you can take proactive actions to give him a paid leave, so he will not cause a problem. So that way, people are advancing the state. So Industry 4.0 is a larger concept. Within that, there are many aspects, as I mentioned, environmental monitoring, lean manufacturing, smart automated factories, and so on. So what environmental impact will Industry 4.0 have? It's a very open question, very difficult question to answer, because right now we do not know what is the impact of Industry 4.0 because of the high automation involved. But people say it saves the environmental aspects because it reduces the waste, it produces less and only the needed amount. It doesn't create a lot of storage unnecessarily. So it may have a lesser amount of items produced as a result of the smart production as well as distribution network. But the bigger impact may be a social impact. Socially, people have job changes required, and the job changes will have a social issue. Now, fourth question: do we need a specialized in-house teams to manage and run smart factory once set up? Okay. So, yeah, I think a good amount of you will work for a good amount of us, not you. I mean, a large number of, as I mentioned in one of my previous talks, something like 80% of all engineers, okay, all engineers in the sense electrical, mechanical, electronics, computers, instrumentation, all people will work in the domain enabled by Internet of Things. Okay. Now, what that means is you may have actual laborers working on the production system limited to bare minimal number. Okay, which means like few people only will be working with that way. All the rest are technical people running the system, designing the system, maintaining system. So that means a large specialized in-house team may be required to do this smart factory, but the factory will run on its own once you do this. Which is the best operating system for IoT devices. So in fact, there are many possibilities right now. TinyOS, Quantiki is one of the good choices for a variety of hardware pieces. And Node-RED is another upcoming thing. I have not mentioned that, which is running very well in various IoT devices. But as I see, these customized operating systems are good for certain hardwares. Okay. On the other side, a generalized low-cost, high-performance hardware platform running Linux may also be picking up very well. So this question 5, which is the best operating system for IoT, is to be answered by time. As you know, right now it's a very fluid state because of the customized hardwares used and the customized softwares used by the industry at large. 6, could you please explain more about Moonlight software? Okay. As I mentioned earlier, first is measuring the mood. Okay. Most of the mood lights available in the market today are not doing that. They ask the user to give input mood. Say, I just want to hear a happy song. Okay. Just want to hear a sad song, or I just want to hear a soothing song or a background lyricless music or lyrics music or whatever. So you have to give the input to the system by manual input and it produces that. In fact, if you see, for example, many of the laptop computers have night light. Night light is actually a different hue of screen light, which is almost like a moonlight. It produces a moon-like thing by the laptop screen. User has to say, yes, the night light has to be turned on from this hour to this hour. So my sleep will be better during that time. Okay. So that way, most of the mood lights available today seek users input. And once the input is available, you can actually have a combination of RGB LEDs turned on to produce appropriate lights for that. In fact, several products are available in this market. Okay, it's possible. The applications of this in business as well as in home are actually not explored sufficiently well. Few years down the line, you will actually be seeing such applications. Okay. Any other question? Yeah. Yeah. Okay. Any other questions?
Sir, we have got one more question. Are you able to see that, sir, or should I read it out?
Yeah, I'm able to see that. So
Okay,
has
sir.
the arrival of edge computing technologies had any impact on the adoption rate of IoT technologies? Actually, the arrival of edge computing technologies is not happening all of a sudden. This is a very slow infusement of edge computing technologies. Even now, it is not really completed. The process is still going, and it is now one of the very active research areas. Okay, what kind of edge computing, what kind of caching, what kind of storage mechanism should be adopted, and so on. So this enhances the response to the user's inputs. Okay, response, because some of the computing is done very close to the users or very close to the sensor itself. Instead of going all the way to California and get it processed there and returning back, you can get it done in your own home itself. So that's where the response time for various decision making process is actually very high. But that way, that did not suddenly impact the adoption rate. Adoption rate of IoT is growing at a rapid rate. In fact, many of the households have IoT devices without the house owners knowing that they are IoT devices. If you have purchased some of the air conditioners recently, uh, you must have purchased an IoT enabled air conditioner only, because that may even provide Wi-Fi. It may give diagnostic data. It may give operating conditions data to the company, and it may give users some sort of flexibility in controlling and using the device. So that way, the adoption. We did not look at whether edge computing is used in an air conditioner which is IoT enabled. So edge computing may have improved the performance of that system without letting a user know that. So adoption comes based on the comfort of or convenience of users, as well as the availability of products or factors like that. A specific technology that improves the response time may have played a role, but the role is actually not very well known outside. So we do not know whether edge computing played a main role, or general flexibility enabled by IoT technology played the adoption better. So, yeah, what would be the impact on IoT on big data analysis? So these are actually very closely related areas. For example, IoT. For just let me give one example. Now, this particular example, I have refrigerators. Refrigerators are produced by some of the major players. So imagine a refrigerator, LG making a refrigerator. Okay, so last year, some of the LG air conditioners may not be IoT enabled. From next year onwards, probably some high priced refrigerator versions may be IoT enabled. But 5 years down the line, maybe they will produce only IoT enabled refrigerator, air conditioners or refrigerators. Okay. Now what happens is they sell in millions of numbers every year. So 2 3 years down the line, when they sell like 10 million air conditioners or refrigerators, so these 10 million devices will be collecting data, diagnostics data, usage data, ambience condition data, fault related data to their factory. Okay, now LG has to have a big data problem in their hand. So they have to have big data analytics solution to make good use of this data. So that way, now the question is, what would be the impact on IoT on big data analysis? So IoT creates need for big data analysis for better usage of the IoT system. Okay, any other
Thank you,
question?
sir.
Yeah.
Thank you, sir. Do we have any more questions coming from the participant side? Okay. I don't think any more questions are there.
Okay.
On behalf of the entire staff and faculty of Department of Electronics at Talkage, I extend my generous thanks to Dr. Manoj sir, who had graced this STTP by giving his vital time from the busy schedule. And the session was very much informative, as the discussed areas were very much relevant with the current technological trends. Thank you so much, sir.
Thank you. Thank you. Pleasure is mine. All the best. Yeah.
Thank you, sir. Thank you. It was a nice session. Thank you so much.
We'll begin the next session at 1:30 p.m. Thank you, participants.
Hello, good afternoon. Lentin, sir.
Yes, yes, I can hear you.
Okay, sir. Welcome, sir, to our STTP. Uh, we can start the session shortly as the participants count. Let we wait for some more participants to join.
Sure, sure.
Okay, sir.
Good afternoon, all. We'll resume with the afternoon session.
Okay, so can I start?
So 1 second, sir. Let me
Okay.
just give an introduction.
Sure.
Yes. So the last session for the day, the session will be on the topic Introduction to Robot Programming Using ROS. And it is being presented by Mr. Lenton Joseph, CEO, Cubotics, Kochi. Lenton Joseph is an author, robotist, and robotics entrepreneur from India. He runs a robotics software company called Cubotics Labs in Kochi, that's in Kerala. He has 10 years of experience in the robotics domain, primarily in robot operating system, OpenCV, and PCL. He has authored 8 books in robotics, namely Learning Robotics Using Python, 1st and 2nd edition, Mastering ROS for Robotics Programming, 1st and 2nd edition, ROS Robotics Projects, 1st and 2nd edition, and Robot Operating System for Absolute Beginners. He has pursued his Masters in Robotics and Automation from India and also worked at Robotics Institute, Carnegie Mellon University, Pittsburgh, USA. He's also a TEDx speaker. We welcome you, sir.
So yeah, so thanks for the introduction, and yeah, we can start. Okay. So before starting today's session, I would like to say something about this session. Okay. So first of all, the thing is that I am actually podcasting this from my home. Okay. So there are a lot of background noises. I'm hearing sound of birds, sound of kids playing around me. So I'm giving an advance apologize for these things, because I can't avoid that a lot of kids are playing around me. Okay, so that is one thing. And also I would like to say something about this session. Like, we will be starting with the introduction of robot programming and ROS. Okay, it's just an introduction. We can't discuss more stuff on this topic because it will take at least 1 week to explain almost all the concept of ROS. Okay, and so if you have any doubts during the session, what you can do is that you can put it in the chat box. Okay, maybe I can stop after some topics and ask you for like queries, like if you have any doubts regarding the session. Okay, so in that time you can use the chat box for interacting with me. Okay, so my chat box is actually open, so you can interact with me using the chat box. And yeah, so this is not a hands-on session, but I can show you some demos. Okay, we have very limited time, right? At least I think I will be taking 1.5 hours mostly, and 30 minutes for Q&A. Okay, so what you can do is that if you have any queries, maybe an advanced question or something, then you can ask at the end of the class. Okay, so so we can start, I think. So the first question is, how many of you already work with ROS? Did you heard about ROS, guys? You can use the chat box to interact. So do you have any previous experience with ROS? If you have, just put it in the chat box so that, okay, so some of you have. So we can just make this session as interactive, because I know 1:30 to 3:30 is not a good time for learning. So I can try my max, because after lunch we will feel sleepy. Of course, even I'm feeling sleepy, but I can make this, I will try to make this as much interactive as I can. Okay, and I can show you some cool videos regarding this topic. Okay, so hope you can I mean, yeah, you can just interact with me so that we will not feel boring. Okay, so let's start. Just a second. So the topic is Introduction to Robot Operating System. It's basically using for robot programming. So again, a little bit about myself that actually mentioned in the introduction. I'm working with this domain, that is robot programming, for 10 years. Okay, I'm mainly using ROS. It's a framework mainly. Using this ROS, I'm actually building stuff, mainly building robots. Okay, and I used to write books in the meantime. From 2014, I used to write books in ROS. Before that, I used to write tutorials, blogs, videos. Yeah. So these are my hobbies actually. And I have a company. It's actually a small company. It's called the Cubotics Labs. It's mainly a service-oriented consulting firm. Basically, we have clients from abroad, so we will be working with them, mainly startups from US. So we will be doing product development, software development for the clients. And also I have a small robotic blog called Robo Academy. So it's mainly for teaching rows. I mean, there are students abroad. There are a lot of people join in my course actually. So these are the things that I'm doing. Like Cubotics Labs is a consulting firm, and Robo Academy is for teaching students about robot programming and rows. Okay, so these are the main thing I'm doing. And regarding my experience, I started working in robotics from 2010 from the academia itself. And after that, I joined in a startup, robotics startup. Then in 2014, I started my own firm. And it's not a big firm at all. It's a small firm. It's like a group of friends. So we are mainly focusing on projects, robotics projects and simulations. Okay. And I have masters in robotics, and as well as I worked a little in Robotics Institute. You may have heard about Carnegie Mellon University. So I have a small working experience in that. And I also talked in TEDx regarding my experience, how I started with robotics, and what are the things that I'm doing now. Okay, fine. So these are some of my books. I'm just showing this. So most of the books are related to robot operating system. You can see it's robot operating system for absolute beginners. That is a perfect choice if you're starting with ROS. Okay, then learning robotics using Python. All the books are related to robot operating system. Okay, so you can find these books from Amazon. And these are some of the books I reviewed. I didn't mention all the list of books, but mentioned 3 of this. Yeah. So that's a thing. So this is the agenda of today's talk. I will be first talking about robot programming. Okay. Then I will introduce ROS. Then if we have time, then we can go in detail, like installing ROS architecture, and ROS communication model, etc. Okay, so I will try to cover almost all the topics. Let's see. Okay. So the software that I'm using is, I think you maybe heard about Ubuntu 20.04. So I'm using Ubuntu 20.04 with a ROS version called ROS Neutic. Okay, so these are the version that I'm using. I mean, I'm using this version to demonstrate the capabilities of ROS. Okay, so we will see that in later slides. So let's start. So again, you already know this, but I just included for introduction. It's like, you know, the primary components of a robot. It's like it's three parts actually. Like there's a sense, there's a think part, and act unit. So basically, the sense is having a list of sensors. Okay, so you can find the camera, you can find the lidars, you can find ultrasonic sensors, and the list goes on. Okay, and what about think? Think means it's like our brain. Okay, so the think module is having the computers. Okay, so there are a lot of computers available that include our laptop, desktop, then single board computers like Raspberry Pi, Jetson. Yes, there are a lot of compute units available. Okay, and the act means the actuators. Okay, actuators is giving life to a robot, right? It's meaning it's like there are list of actuators available, like DC motors, servo motors, stepper motors. So there are wide variety of actuators available. So basically a robot, even if it is a if it is a small robot like line follower, or if you take an advanced robots like you maybe heard about sport robot. We can call it as an advanced or complicated robot. If you take both these robot, you can find these blocks. Okay, so these are the important blocks of a robot. Okay, and basically what a robot does is that it is having the sensor readings, and it will feed that sensor reading to a computer that is in the think part, and the computers is actually controlling the actuators. Okay, so that is actually present in the physical robot. I think these concepts are clear to you. Okay, it's very simple. So this is a sense, think, act loop, which is basically taking the sensor values, then taking a decision on the think part, then acting accordingly. Okay, so this is a basic block diagram of obstacle avoidance robot. So there is a sensors available. So it will detect the obstacle, and it's saying, hey, the wall is 5 centimeter away from me. Okay, and this sense value is feeding to the think. Okay, so what thing does is that, oh, it is too close. So what did I do? So it will take a decision based on this sensor value. So the think session says, hey, there is an obstacle and you have to move away. Okay, and it will feed that control signals to the actuators, and what the robot does is that it will move away from the obstacle. Okay, and these loops keep on doing. Okay, so this is a basic example of a sense, think, act loop. Okay, and this is a broad overview, I mean inside view of a robot. You can find a list of actuators, list of sensors in the robot, and also the main part is a think. Okay, so in this talk, in this session, I am focusing on the think part, that is the computers. Okay, so in the computer you can use a microcontrollers, you can use a PC or single board computers, or a motor so these are the compute unit, and you can control other stuffs like motor controller from this microcontroller or PC. Okay, so we are focusing on the PC microcontroller, that is the think part of the robot, because we are going to program the robot. Okay, so in order to program a robot, we have to program the computer inside this robot. Okay, so that is our aim. Okay, so these are the main components of a robot. Basically, the sensors, actuators, computer, and these are some of the examples. Its camera is the wheel encoders, ultrasonic sensors are the examples of sensors. Then there are actuators, the servo, stepper, DC motors. Then the compute unit. So you might hear about NVIDIA TX2, Intel NUC. Intel NUC is a miniature size full desktop PC. Then we have also the microcontroller platform like Arduino. You have heard about Arduino, right? Then Texas Launchpad, ARM-based controllers, STM32 boards, lot of list. Okay, so I have just put this list of actuators for your information. You can see the servo motor, stepper motors, DC gear motors, dynamics of smart actuators. Those are very expensive, guys. Like if you are planning for very accurate application, I will prefer to use a dynamical smart actuator. Sorry. Those are very expensive, and it is having everything like PID. Then there are inbuilt settings available. So yeah, so there are wide variety of actuators available. Okay, and of course industrial servo motors. If you find the automation robots like in the car manufacturing or production environment, we are using industrial robots, right? So they are using these kind of servos, industrial servo motors. Okay, and these are some of the popular sensors available. If you heard about self-driving cars, then you might have seen this sensor called Velodyne. Okay, so these sensors are the top of these self-driving cars, which is actually rotating and gathering the 3D information around that environment, I mean around the car actually. So that is actually helping the self-driving cars to navigate. Okay, and there are other sensors like laser scan, depth sensors, then even small sensors like ultrasonic, then sharp distance sensors. So these are all included in the sensor, and these are the computing unit that I mentioned. I just put the diagram to understand easily. This was a compute module, Intel NUC. This is very portable. The reason why I included this is if you're planning to prototype a robot, you can use these modules because these are very small. Okay, and also the weight is also not high. Okay, so you can easily put these modules in your robot. Okay, what about like thinking, I mean, if you're putting your full size desktop CPU on the robot, then it's very difficult because it's way much heavier, right? So you can look on the alternative like NVIDIA TX2, then Intel NUC. These are x86 PC only, and NVIDIA TX2 is an ARM-based platform, but still it is having most of the things, okay, that you need. So these are the options that you can use for the Think unit. Okay. Now we are coming to the robot programming. Basic. What is it? I mean, basically we are talking about we have to program robots, and what are we doing with this robot programming? In a simple sense, we are actually modeling the behavior of the robot. Right? Like we are using some programming language. Okay, it may be C, C++, Python, or any programming language, and we are trying to model the behavior of the robot. Okay, and the input of this model will be the sensor values, and the output will be the control signals that is feeding to the actuators. Okay, so what we are doing is we are creating this model, okay, by using some programming languages. Okay, it's simply we are creating the behavior, how to behave in some situation. Like if we are getting some sensor value in certain range, then behave like this. Or if the sensor value, if we are not getting the sensor value, then behave like this. So in robot programming, we are basically modeling the behavior of the robots. Okay, and commonly we can use any programming language to model the robot behavior. Okay, but mostly the popular programming languages are C++ and Python. Okay, I'm mainly using C++ and Python because these languages have a lot of interface to other software libraries. The software library means if you want to do some image processing, okay, then you can use a library called OpenCV, Open Source Computer Vision. And if you want to perform some point cloud based operation, like point cloud is a 3D representation of the environment, you can use point cloud library, that is PCL. So if you take most of the libraries, it is having a connection or interface to C++ and Python, meaning you can program or you can use that library in this programming language. You can include the header files of that program of that library in C++, and you can simply call the functions inside that library. Okay, so if you take OpenCV, it is having C++ and Python bindings. Okay, so mostly the popular programming languages are this. And I just included this slide. It's like it's an advanced points actually, but I can mention. So how to choose a programming language for your robot. Okay, so imagine you are doing a robotics project and you are going to program it. Okay, so what are the main features that you have to taken into consideration when you program a robot? Okay, so if you are from computer science background, I mean a little computer science background, then you can understand these concepts like threading, high level, and object oriented. You might heard about object oriented concept, right? And it should be very easy to prototype. If you take Python, for example, It is very, very easy to program compared to C++. And it's also like it should perform well, okay? And it should have some capabilities to do in the process communication. Um, if you are working with a complex robot, you should have some capabilities. The programming language has some capabilities to communicate with different programs. Okay, we will get back to that. And you should have a good community support. Then third-party library that I have mentioned about the OpenCV. Okay, then it should have some support for the existing robot framework. So these are some of the factors that you have to take into consideration while working with robot programming or choosing a right programming language for your robot. Okay. So if you are trying to program your robot, there are two approaches simply. What you can do is that you can simply take some existing software framework to program the robot, or you can write the code from scratch. Okay, it's very simple. Like, the existing software framework means the software frameworks are already available, okay, so that you don't need to work hard. Instead of that, you can simply take that framework, do some customization, and your robot is ready to go. Okay, so this is the first approach. Simply, I think you got the point. And the second approach is you're writing everything from scratch, meaning you are choosing a programming language and you are writing the code, the program, or the software for the robot from scratch. So, the first method will not take much time. It's actually taking an existing framework. But for the second method, it will take a lot of time. But each approach has its own advantages and disadvantages. Okay, I will prefer the second method for product development, long-term product development. If you are looking for the prototype, then I think we can start with the software framework. Okay, so ROS is actually a software framework for robots. Okay, so that is the main point that we are going to discuss in this session. You also heard about Arduino. Arduino, you heard about. It's a popular embedded board programming language, right? Arduino. So it's again a framework. They actually given a framework to us, okay? And you can program based on that. So ROS is one of the existing framework for robots, okay? And we are going to discuss more about this approach. That is, we are taking the existing software framework and customize it and deploying it in the robot, okay? And so what are the existing software framework available? We have ROS, okay, and we have OpenCV, that is open source computer vision. Then the PCL, that is Point Cloud Library. So I have mentioned that, and these are all open source and free to modify. Okay, so you can have a look on to these software frameworks, which can be used for robots as well as image processing application or 3D point cloud applications. Yeah. And these are some free simulators available that will help you to program robots. It's called Gazebo. It's a free robot simulator. Okay. Then there is OpenRave. That is again another framework. And this is again a list of simulators available. Actually, the first simulator is not proprietary. It's actually free simulators available. You can just check and you can download it for free. VRUP is also free, but there is a proprietary version available. And there is another robotic simulator called Acting. Okay, so these are some of the robotic simulators available. Again, popular programming language, C++, Python, Java is also using, and MATLAB. In academia, I think MATLAB is mostly used. Okay, so now we are coming to the prerequisites to learn ROS. Okay, we didn't discuss about ROS yet, but what are the prerequisites to learn ROS? The thing is that in order to start with robot operating system, you should have some idea about Linux, Ubuntu operating system, right? So you should have some idea about working with Ubuntu and also the Linux commands. Okay. And also you should have knowledge in C++ or Python. That is mandatory because you're going to program using this framework, right? Yeah. So, and also like there is another framework like Git, for version controlling. So you also need to know this. Okay. So I'm just giving this a topic because you might think about like why we need a computer on the robot. You might think why we need a computer. We just need a microcontroller. Like if you work in a for example line follower robot, you're not using computer, right? You are not putting a PC or laptop on this robot. It's a very simple robot, right? So in case of line follower, we are not using PC. I think some microphone is not muted. Can you just mute, Neeraja? Okay, great. So if you take the case of line follower robot, we are not using computers, but we are only using microcontrollers. Okay, but if you take an example for an advanced robot like Asimo, you heard about Honda Asimo robot, right? The biped robot. So that is having a lot of computing modules actually. Okay, so if there is a computer, then there should be an operating system running on it, right? Okay, so it's like we are actually putting a computer inside a robot. Okay, so this is actually happening. We are interfacing the sensors to a computer, and there is an operating system running on it. It may be a PC or single board computer, and we are controlling the actuator from PC. Okay, so this architecture that is using operating system or a fully fledged PC, we can control advanced robots. Okay, not just this line follower robot. For controlling this robot, we don't need a full-fledged PC. Okay, we just need a microcontroller. Okay, so these are some of the OS that we are using in robots, mainly Ubuntu, mainly Linux variant. Okay, and also real-time operating system like QNX, VxWorks are using. Okay, so Abhijit, there is having a question. Can we have the slides? Yes, I will try. I will try to convert it to PDF. Yeah, I can send. Okay, so we can start with the robot operating system. So before starting, I would like to say my story. Okay, so this is how I started with ROS. Okay, so this was taken, I think this image was taken in 2010. Okay, and this was my final year project in BTech. Okay, it's called a social robot. Basically, I named the robot as Robin. Okay, and what it does is that it is having the ability to speak, ability to hear, then it is having image processing capabilities, some sort of AI capability. AI means pattern matching techniques only. Then so there's speech recognition, then speech synthesis, then image processing. These steps are there. So I have started my robotics journey from this project. Actually, I officially started working on robotics from this project. Before that, I was working with embedded stuff, then programming. But robotics is a field that I can integrate all of my passion. Like I was very interested in embedded programming and also like the general programming like C, C++. So in robotics, I can integrate all of my interests. That's why I started with robotics. So while I'm doing this project, I have faced these challenges. Okay, so you can see various components present in this robot. You can see two eyes, that is actually webcam, and you can find a here that is actually it can rotate like our head. It's like an animal head. Okay, and you can see the ears. It can the robot actually expressing its emotion using these ears, and there is a lips. Everything is there, like an animal head. Okay, and I'm using two laptops here. One is running on Ubuntu and one is running on Windows. Then it is having 12 servos. Then I have used Python, C++ for this project, and it is having the features that I mentioned. So what are the challenges I faced? Okay, so these are some of the challenges that I faced. The problem is that this project is actually pretty complicated because it is having a lot of features. Okay, a lot of capabilities. So how do I implement all these capabilities? And at the same time, some programs in the robot have to communicate with other programs. Okay, so there should be some communication between programs. So these are the challenges that I face, because there are 4-5 programs running in parallel, one in one laptop, and maybe 2 programs in running on second laptop, and these programs should be able to communicate. Okay, then the task has to synchronize, and also my code was not very modular. There is no specific structure, and if anyone want to create an application on the top of this robot, it's nearly impossible. Okay, so these are some of the challenges I faced, and this was a software communication diagram. Basically, I have implemented a TCP server client architecture. You might hear about the server client architecture. Like the server is a program, and the clients are it can able to communicate. Okay, so the round seeing is each programs. Okay, so I have different program for different application. Okay, for computer vision I have a client, for speech processing I have client, and artificial intelligence and everything I have a client, and there is a sender program called server. Okay, then after that, this the project that I work here was not work with robot operating system, or I just created from scratch. Okay, but in 2014 I created this robot. This is basically a robot working with ROS. Okay, so you can see this is called an autonomous mobile robot. Okay, and you can find the compute module, the Intel NUC here. You can find the Xbox 360. It's a depth camera, and you can find some embedded controllers and drivers here, and also an ultrasonic sensor. So there is no I didn't face any hurdles when I used ROS. Okay, and you can find the list of sensors available on this robot. Like there are 3D sensor, microphone. Oh, there are a lot of disturbances. Just a second. Sorry for that. I mentioned that there are a lot of disturbances happening outside. Anyway, the purpose of this robot was autonomous navigation. It's called the chef bot. Basically, I can use this robot in restaurants for serving food. Okay, so I have used ROS for programming this robot, and there is no difficulties faced. These things are solved. Okay, so this was the starting experience while working with ROS. Actually, when I prototype a robot without ROS and with ROS. Okay, and let's see what is actually robot operating system. Okay, it's basically an open source robotic framework, meaning the code of this software framework is open. You can check the source code of this framework. Okay, and it's a software framework. I think if you are from electronics and communication background, I'm not sure you have heard about software framework. Even I am from electronics and communication background. My bachelor's, I took ECE, and then I took the master's in robotics and automation. So the software framework means it is a collection of functionalities. Okay, functionalities means like if you want to do some image processing application, you can use OpenCV framework, which is having some already predefined functions to do this image processing. Okay, so that's what we call the software framework. It is having inbuilt features. Okay, so you don't need to implement everything from scratch. Okay, so ROS is a software framework, robotic software framework, and the name suggests it's a robot operating system, right? So you may be thinking that it's an operating system, okay, but in reality, it's not an operating system. It's a middleware, meaning it's a layer between software and the hardware. Okay, so this is actually a middleware which is actually acting between the real hardware and the software. Okay, so it's not a real operating system, it's a middleware, and it's need a host operating system to run. Okay, so ROS has to be installed on an operating system. It may be an Ubuntu, it may be Windows, it may be Mac OS. Okay, so guys, these are some basic things. I will be coming back to demo, so you don't need to leave, because I think most of them are thinking like these are simply a theory-based class, but it's not. I'm coming up with cool demos and videos. So these are some start. Okay, this is just a start. You can see some interactive things after a few slides. Okay, so don't worry, this is not completely theoretical class. Okay, so okay, yeah, so what we are discussing was ROS is a middleware, or we can call it as a software framework, and we are installing this framework into an operating system like Windows or Linux. Okay, and you can check the website of ROS. Maybe I can just quit this slide. Let me take the website so you guys can able to hear. Let me take just a second. So if you can just go to ros.org, you can find the website. Okay, I'm just sharing the link. So this is the official website of ROS. Okay, so you can find the definition of ROS. It's here itself, and there are instruction to install this, because I mentioned in the definition itself, this is a framework. We have to install it in some operating system. So the latest version of ROS is Noetic. Okay, I will explain this in detail, but I'm just showing the website and all. You can just take this website and just have a look. Okay, so I'm just coming to the presentation. Okay, yeah. So what is ROS? That is a main question that we are going to address in this session. So ROS is having 4 sections. Okay, I mentioned that it's a software framework. And what is the core part of ROS? So that is very simple. ROS is actually helping us to communicate with different programs in your PC. For example, you have a program that you may be using C or C++ or Python. Okay, you have a program called program A. Okay, and you have another program called program B and program C. Okay, and using ROS, what you can do is you can interact with this program. Again, some disturbances. I'm just muting. Just a second, guys.
Hello, sir. Okay.
Sorry, guys. Actually, there are some. Anyway, like that is fine. So we can explain from here. So I mentioned that this ROS is actually helping us to communicate with different programs. Okay, so for example, you're running several programs in your computer. For example, 5 programs in your computer. So using ROS capabilities, what you can do is that you can use ROS to communicate with each other. For example, here is his 3 programs, okay, that is running on your computer. And what you can do is your first program can communicate with program 2, then the second program can communicate to program 1, then in any manner it can communicate. Okay, so what basically ROS does is that it is giving some functionalities, okay, in order to communicate with different programs. Okay, so why this matter? You may be thinking, for programming robots, why this actually matters. It actually matters because when you work with actual robots, then you might have to write different programs to handle different sensors, different actuators, and different applications. So that's where ROS is relevant. Okay, so basically this framework help you to communicate, help your programs to communicate with each other. It can send data, it can receive data, it can store some information. So this is ROS basically. The term that we are using is inter-process communication, meaning different programs can interact with each other, okay, and exchange data. So that part is actually called the plumbing. Okay, the inter-process communication, that part is called plumbing. Then ROS is providing us with different tools. Okay, so this is how an inter-process communication picture looks like. Each this is actually a node. Okay, you can say these are individual programs, and this program is communicating this, and this program is communicating to this in different ways. Okay, so this program is communicating to this in 4 channels. Basically, it is actually sending different data to this program. Okay, so basically ROS help us to communicate with each other. Different programs can communicate with each other and exchange data. Okay, and along with this inter-process communication, it is providing us with some tools in order to debug and in order to visualize the sensor data. For example, if you check this diagram, this is actually a tool called RVs in ROS, okay, which is basically help us to visualize the sensor data. Sensor data means if you want to visualize a camera image, you can do this. You can use these tools to visualize. Okay, so that is the second part, the tools. Then third part is the important thing. So I will show you some interesting videos of this. That is upcoming slide. Capabilities means the ROS is having some inbuilt packages or software in which you don't need to code at all. You can simply take these packages and just customize it, and it's ready to go. For example, if you want to develop an autonomous mobile robot, okay, so the term autonomous mobile robot means it can able to go from A to B. Okay, the robot can go from A to B autonomously without hitting anywhere. It is doing by avoiding obstacles, and it is taking care of everything. Okay, so if you want to build a robot like that, you can simply use ROS. Okay, the existing packages or software is there. You can just customize it for your robot, and it's ready to go. Similarly, if you're working with a manipulator like a robotic arm, you might work with robotic arm, 7-door arm or 6-door arm, 3-door arm manipulator. That is robotic arm, like our hand. If you want to work with a robotic hand, then there is a software, an existing packages available in ROS. So just take these packages, customize it, and your robot can move. It can do inverse kinematics and forward kinematics. It can do obstacle avoidance, anything. Okay, so that's what I'm showing here on this diagram. I will show a cool video of that. Okay, so that is a third part. And what ROS is having is, it is having a lot of developers worldwide, and they are providing a lot of tutorials, Q&A. So if you are planning to work with ROS, then you will get a lot of support. Basically, that is what we meant by ecosystem. Okay, so there are a lot of developers that is working with ROS. Okay, that is including me. Okay, so these are the 4 core points of ROS. Okay, so we have seen what is an inter-process communication basically. So this is what we meant by this. Okay, and this is a practical example. So here there are 3 programs. Okay, so these 3 different programs, and the first program, what it does is that it will access the camera that is connected to a robot and sending the images. Okay, so using ROS we can send any kind of data between 2 programs. Okay, so the first program is sending images to the second program. Okay, and what second program does is it will receive the data from the first program and perform a face detection. Okay, so when you do the face detection, we will get a centroid. Okay, centroid of the face. Then that the centroid will be sending to another program. Okay, so there are 3 programs and 3 are communicating. Okay, so this is a practical example. Now we can have a look on to the tools. It's called RVS, RQT. Then there are command line tools. I will show that. I'm just skipping. So this is the RVS. It's actually a 3D visualizing tool in order to visualize camera data, lidar data, and even robot model. And RQT, this is another tool from ROS, which is helping us to debug, visualize, plots. You can see this. Okay. Now the important part, the capabilities. Okay, so first I'm talking about the ROS navigation. Okay, I already mentioned that navigation is simply going from A to B. Okay, so let's see what is a ROS navigation. You can see a video here. I hope you can able to see the video clearly. So in this video, it's actually demonstrating the ROS navigation. Basically, I am commanding the robot to go to B, that is the goal position. So the robot is going from A to B. This is actually a robot called MIR. So the simulation and everything, the software is available in ROS repository. So you can also try it out. So basically, this is what we call an autonomous mobile robot. Okay, so I think the video is having some issue. Okay, so now can you able to see, guys? Is there any issue with the video? Please let me know so I can show it again. Can you see my screen, guys? Anyone? Okay, great.
Yes, sir.
Okay. So currently I'm showing the video of navigation, autonomous navigation. I hope you can able to see the screen also. Like you can see the robot and you can see the path plan by the robot. Okay, if you give a goal position, then what robot does is that it will create a path. Okay, then it will try to execute this plan. Okay, so these things can be done using ROS navigation stack. Okay, that is the one capability of ROS, only one. Okay, there are many capabilities. Okay, that is coming. The second capability that I'm planning to cover is ROS manipulation. So this may be you guys may be working with. Okay, you may can. I think okay. I think my network is okay. Maybe you guys can check. Yeah, if there is if you are not getting anything, just mention in the chat box. Okay. So now we are discussing about the manipulation. So if you are working with a robotics course, I mean, if you are taking any books like Introduction to Robotics or any books, they may be starting with a manipulator. Okay, it may be a robotic arm. Okay, so if you're planning to work with a robotic arm, then you can either work from scratch, that is mentioned in the books. You can find the DH parameters and calculate everything. Yeah, that is one way of doing. Okay, and if you're not planning to work with these things, you can use these existing stack. Sorry for the excess sound. Let me mute my volume. Just a second, because the video is having a lot of sound. Just let me reduce the sound. Okay, I hope this is okay for you. Okay, yeah, so guys, you can see this video, right? So basically I'm showing a robot is actually picking a box. Okay, and on the right side you can see the tool called Avis, and using some markers, it's basically detecting that box and putting on a platform. Okay, so this is basically an IK problem, right? This is like it is detecting the box, then it is picking that box. Okay, then it is taking another box, you can see. So on the robot there is a camera. Okay, so that camera, using that camera, it is detecting the box. Okay, you can find how it is taking. Okay, and it is putting on the top of the box. Okay, so this is an example of rows manipulation. Okay, you can do the inverse kinematics, forward kinematics, everything. The packages are already there. Okay, and you can also develop your own IK solution. Okay, I think you maybe heard about inverse kinematics and forward kinematics maybe in the previous lectures. So these are already implemented in these packages. Okay, I'm not saying that these are super easy, but you should know the basics of rows, and if you follow some tutorials regarding this manipulation, you can achieve this IK working on your robot. Okay, without writing any single line of code. Okay, now I'm showing another capability of rows. It's called the perception. Okay, so the perception, from the word itself, the things that we are perceiving, the perception. Okay, using perception, robotic perception, you can do a lot of things. So here it's an interesting video. Let me full screen. Yeah. So this video is actually showing the mapping of sorry for that, mapping of a city. Okay, using an autonomous self-driving cars. Okay, you can find it is actually creating the 3D 3D model of the city. Okay, so this is actually using in self-driving cars. Okay, so you can also create this kind of models from rows. Okay, so this is called the point cloud. I mentioned about PCL, right? It's using that library you can create this kind of 3D point cloud representation. Okay, yeah, so we have covered three capabilities, important capabilities, that is navigation, manipulation, and perception. Okay, so it's already there. Okay, so you can just take these packages from rows and you can work directly with your robot. And if you just have a look on to the statistics of rows users, this is actually an old metrics in 2017, but a lot of people are using rows in US, China. Then if you check in India, it's in 5th position. You may not be heard about this framework, but these are using in robotics. Okay, in India also a lot of institutions are using this framework. I personally know in IIIT Hyderabad, IITs, and also in non-IITs organizations, they're also working with this framework. Okay, yeah, and I just want to mention the official tutorial of ROSE. So in this talk, I can't cover all the aspect of ROSE, but just giving an introduction. Okay, so this is the official website of tutorials of ROSE. I'm just sharing the link, guys. You can just take it. It's called the wiki.rose.org. Sorry. So in that, you can find the instructions for installing, getting started, tutorial, then yeah, a lot of things. Okay, but the problem is that as a beginner, I will not prefer to start with wiki. Maybe you can have a look onto some tutorials, other tutorials, because if you're reading Wikipedia, then you should have a lot of tabs open, because you are reading one topic in Wikipedia, and what happening is that you may be clicking some other link, and you will get another page. So similar to that, for ROS wiki, you may be encountering that kind of thing. So if you're a perfect absolute beginner, then you can look for other tutorials. Okay, so this is actually a good a website to get the ROS tutorial. But if you're an absolute beginner, then you can go with a book, then a video or course or something. Okay, so that is the wiki.ros.org. Then, so these are the operating system that officially supported ROS. Okay, so if you're planning to work with ROS, then you will get support. And now you can install ROS on Windows, but it's pretty complicated, but still you can do. Okay, so if you're working with Ubuntu, you can easily install ROS. Then you can install in Mac. There are a lot of OS support now. Okay, so this is the things that ROS having. We have a middleware that is helping our programs to communicate with each other. Then there are tools that we already seen. It's RVs, RQT, the libraries, client libraries, lot of stuff. Okay, so just have a look. And okay, so from the next topic, I'm just focusing on to the ROS stuff, but I just want to give an idea. So what happened before ROS and after ROS? Okay, so this ROS framework is actually introduced in 2007, okay, in Stanford. And after that, there is an organization called Willow Garage. They actually taken this framework and did a lot of modification. Okay, so they actually named these frameworks as ROS. Okay, now it's actually an maintaining by an organization called Open Robotics. Okay, so what happened before ROS and after ROS? Before ROS, there is no common software development platform for robots. Okay, and the code reuse was also very difficult. So if you are using ROS, the code reusing is very easy. Okay, so before ROS, maybe if I am planning to work with a robot before the ROS framework, I will be writing a code for my robot from scratch. Okay, so the problem is that I will take a lot of time. Then the cost of development is very high, and yeah, so a lot of things associated with that. But after ROS, what's happening is that we can reuse a lot of things. Okay, so just look at the navigation part. You don't need to code at all. You can simply take that packages and customize it, and it's ready to go. Okay, so that's what's advantage of using ROS. Okay, so you can reuse the code. Then collaboration of this project is easy. Okay, so there are a lot of advantages of using ROS. Okay, now I'm just going through who created this platform. Okay, actually the project started from Stanford. Okay, at that time the name of this project was Suchiad, and after that after that, there is a team called Willow Garage. They have actually taken this framework and started the ROS project. So this guy was the main guy who started the framework, called Morgan Quigley. Okay, I personally met this guy in some conferences. So yeah, so from 2008 to 2013, Willow Garage is actually they did a lot of changes, modifications, add-ons to this framework. They did significant development on ROS. Okay, so these are some of the robots from Willow Garage, PR2 and Turtlebot. Okay, then now ROS is maintaining by Open Robotics. Okay, if you just go to Open Robotics, maybe I can take the link here. We can find the things that this foundation is doing. Here it is. Okay, maybe I can share the link. So these guys are currently maintaining Open Robotics. Okay, currently maintaining ROS. Sorry, I just yeah. I hope you can able to access this. Okay, so that is about ROS. Who created this is a team behind it. Okay, so these are the advantages of ROS. We already seen code reuse, modularity, then free and open source. If you are building a product using ROS, you can do. There is no fees associated with it. Okay, it's completely customizable. Then you will get great community support. There are a lot of people are working with ROS. Okay, and also it's scalable. You can install this in distributed computers, and yeah, so you can do a lot of stuff. Okay, now we are coming back to the ROS distribution. So do you heard about Linux distribution, guys? Anyone heard about Linux distribution? If you heard about Linux distribution, just comment. Anyone heard about Linux distribution? Guys, are you sleeping? I'm not sure you're sleeping because it's not a real class, right? Okay. So you heard about Windows distribution, right? Windows 7, Windows 8, Windows 10, right? That yes, you are familiar with. Okay, great. So similar to that, Linux is also having distribution, meaning Linux is an open source operating system and you can customize it. Okay, so I can take the code of Linux and I can customize it. I can distribute with my name. Okay, Lendin OS, something like that. You can also do it. Okay, so similar to that, Linux is having, I think, 800, 900 distributions available. Okay, so what distribution means is that it's actually a version set of programs. Meaning, for example, if you take Windows 7 or Windows 10, it is having some set of softwares, right? Okay, so certain version of software. For example, if you take a simple application that is MS Paint in Windows 7, the version may be 1.8, but in Windows 10 it may be 2.1, meaning it is having different versions. Okay, so in Windows 7 we will get an old version, and in Windows 10 we will get an upgraded version. Similar to that, in a distribution means it will have a certain set of software with a certain version. Okay, so we are calling it a distribution as a versions programs, version set of programs. Okay, so if you take Ubuntu 18.04, we will get a set of version software, and in 20.04 we will get an updated versions. Okay, so that's what distribution means. So in ROS also we have distributions. So maybe I'm just going through different distributions of ROS. Okay, from 2010 is Box Turtle. You can see this letter is actually changing, and you can also see the Ubuntu supported. I mentioned that ROS is actually fully supported in Ubuntu operating system. Okay, so these are some of the latest versions. You can find ROS Furate, ROS Groovy, ROS Indigo, Jade, Connected Cane, Luna, Melodic, and this is a final version of Rose. Okay, so this is a latest version of Rose. Okay, and it's called the Rose 1. Okay, I'm using Rose Noitic for the demos and all. And there is another set of Rose called Rose 2, which is an enhanced version of Rose 1. Okay, so the current version of Rose 2 is Rose 2 Foxy. So there are a lot of differences between Rose and Rose 2, mainly the security, real-timeness. There are a lot of improvements in Rose 2. Okay, so these are the distributions. Okay, now some interesting things, like some of the robots that is working using Rose. Okay, so I talked about Rose, interprocess communication, a lot of things. So now you can see some robots that is working using Rose. Okay, you can find the PR2. So this is completely running on Rose. Then Turtlebot 2. Maybe if you have a robotics course in your institution, you can buy these kind of robots because these are very cheap, and it can be used for education. Okay, and these are some of the other robots. I think it's mostly expensive, but it's still using in research. Okay, research and product development. And you can see here a Robonaut 2, which is from NASA. They actually use Rose for the software. Okay, but after that they changed to some other, but for prototyping they have used Rose. Okay, so these are some of the robots that is using Rose. The list actually continues. I just put some robots, and now I just want to show you a video demo. Just watch. I hope your network is okay. In this demo, I am actually showing an application. It's actually a simple application. It seems like simple, but it's not very simple. So this video is taken in in Willow Garage in 2010 or something. What they did was, these engineers did was they created an application using Rose, and you can order beer or drinks from the fridge, and the robot can deliver in your where you are sitting. I mean, yeah. So this program, maybe I can just increase the voice a bit. Let me just a second. Let me increase the voice a bit. Yeah. So this is one application. I mean, this just watch the demo. So they have created a web interface so that you can select the beer that you want, and the robot will deliver. Okay. See the things that robot doing. It's actually opening the fridge and taking the beer, but it's actually running on 6x, so it's very, very slow. But just imagine the capabilities that the robot doing. So it is using the manipulation packages in Rose as well as the navigation. Yeah. So after that, it's delivered. Okay. And also it can open the bottle. Right. So this was basically a hackathon. So one of the application that they did to demonstrate various capabilities of Rose. Okay. This is another demo that robot is playing pool. Okay. So you can see it is playing pool. So they have created a software application based on Rose, and the robot can able to play pool. I think it can play pool better than us, because the computation, they are using an algorithm to path plan. So we can't do that because we are doing everything in our mind, right? So, but they're actually having an algorithm. They will detect the balls and they will iterate the path. Like if the robot hit the white ball, then where it goes, that can be simulated. So in each angle, it will simulate. Okay, so it is having that capability. So actually, this actually didn't done in 2010, I guess. So now you can imagine it, now we are in 2020. Just imagine robot capability or ROS capabilities. Yeah. So I just show you to understand the capabilities that we can build on your robot. So in this video, what they're doing is they are creating a cooking demo. Basically, I think it's robot is cooking the popcorn. Okay, and it's doing perfectly. I mean, it is taking time. It is actually taking a lot of time, but still it is doing very well. And it's not hard coded. It's not like scripted or something. The robot is actually taking the values from the sensors, and yeah, it's pretty good actually. And it's taking the plate to serve, I think. You can see the laser scanner on the chest. It's actually using for detecting things. It can even put the pepper on the top. So just imagine the accuracy. And yeah, so if you want to do this kind of application, the software is also like well refined, otherwise it will fail. Okay, so everything is doing using ROS. Okay, yeah, and some other demos are using navigation. So this is a demo of the ROS navigation stack again. So you can see the robot is moving, and if there is an obstacle, it will move away from the obstacle. Okay, so this will be doing automatically. Okay, and also you can find it is actually creating the map of its environment. Okay, so you can see it's how accurately it's moving around the obstacles. And you can see in a final demo of this, like this one. The robot is actually moving and there is a dynamic obstacle. And what the robot does was, like, it just stopped and path planned to a different different area. Yeah. Okay, I think you got an understanding about ROS capabilities now. This is again a video of ROS turtle board. Okay, it's basically it can be used for education purpose. I think it's cost around 1.5 lakh or so, but you can prototype this robot in your lab. Okay, the designs are open, so you can prototype this kind of robot. Okay. Okay, so those are the demos of ROS-based robots and its applications. Now we can see some sensors that is supported rows. Sorry. You can find some lidars, laser scanners. These all are supporting rows, meaning you can plug the sensor on your computer and you can access the sensor value in rows environment. You can just send this value sensor value in different programs. Okay, you can send images, you can send laser scan, you can send any data between two programs. Okay, these are some of the sensors board supporting using rows. Okay, and these are some of the libraries that is supported with rows. You will get OpenCV support. For example, if you want to perform a image processing application, you can either use OpenCV simply without using rows, but if it is in a robot, you can use the interface, OpenCV rows interface. So that is basically enables you to work with OpenCV library, and you can also send images between different programs. For example, one program is reading images from camera, and it can send to multiple programs, and each programs can do different applications. Okay, and coming back to the important things. So why you are learning rows? What are the importance? What will you get? So that is an important question, right? So if you check in most of the companies, like big companies like Intel, then Qualcomm, any companies, they actually use rows for the projects. Meaning, if you take NVIDIA, for example, NVIDIA is a graphics card manufacturing company, right? So these companies mainly also working with AI and robotics. Okay, so they had some interesting contribution to ROS, and they are also working with ROS. Okay, and you can find most of the companies like Bosch. Then in India also, TCS, Wipro, they have their own robotics wing. Okay, so those companies are also using ROS. Okay, and if you are a student, then the advantage of using ROS is you can prototype your application in ROS, okay, for your final year project or mini projects, anything. Or if you're a researcher, for example, if you are doing PhD, the advantage is that you may be focusing on a very unique topic. Okay, so for example, you are planning to create an inverse kinematics algorithm. Okay, so for that, you need a robot, you need a simulation, you need something, right? You need a lot of components, but you have to focus on the IK. So in that case, you can use rows, and you can set up all the things using rows, and you can only focus on the IK part. Okay, so that is the advantage of using rows. Okay, and even companies are started using, even Cubotics is an example. We are mainly into the solution domain, but there are products that is using ROS. Okay, and there are hobbyists, roboticists, hobbyists are also there. They're using ROS for their prototypes. Okay, and regarding the job opportunities, if you check in robotics engineer or robotic software engineer related jobs in such site called Glassdoors or any site, you can find ROS as a requirement in their experience. Okay, so ROS is getting one mandatory requirement for robotics engineers. Okay, and so what is the future scope of this framework? The thing is that if you take a computer, if there is no operating system on it, like if there is no Windows or Ubuntu, anything, it's just a piece of hardware, right? But what the like a software is giving life to this hardware, right? We are actually installing an operating system on the computer, and then we can start working on it. Similarly, for robots, without any software or without any program. It's just a piece of software, a piece of hardware. Okay, so software, like the computer software, robotic software is also important. It's also like it is having great value nowadays, because using a single robot you can do a lot of things. I mean, the scope is infinite. Okay, so ROS is actually a framework for the programmers to prototype and deploy robotics application, okay, for any robots. Okay, and regarding the opportunities, there are a lot of robotics developers are coming, and ROS is one of the important skill set in companies, and it's becoming a standard in robotics programming. And if you want to explore more in ROS, there is a ROS conference. I have attended ROSCON 2019 that was happening in Macau. So you can find a lot of interesting talks, okay? Interesting talks, latest technologies or latest updates regarding this framework, okay? And this was one pick taken with the CEO of Open Robotics. So this was actually my book release called ROS Robotics Project Second Edition. So I have taken this in ROSCON 2019. You can also find the old talks of ROSCON. You can find there's a site called roscon.ros.org. Maybe I can give the link. You can just have a look on to that. It's roscon.ros.org. Okay, you can have a look onto it. Okay. Yeah, and also you will get support from ROS Wiki, ROS Answers. Okay, and also there is a blog called, it's not a blog, it's a forum called discourse.ros.org. Let me take that website. It's actually very interesting. We will get updates of ROS. Maybe I just put the link, can also show that. So this is like a forum. You can find latest updates of ROS framework. Okay. Yeah. And now the installation. We have limited time, but I can mention how to install ROS. Okay. Simply, if you want to start with ROS, just go to ros.org, and for example, if you're working with latest Ubuntu distribution, you can work with ROS Neutic, because ROS Neutic will support 20.04, and you can select Ubuntu. Then you will see some instruction. So just copy paste, okay, and you can see. You can install ROS. Okay, so this is a basic installation instruction. Okay. Yeah, and let me see if I can cover anything more. Maybe I can do the demos after this. Yeah, I think this will be enough. We have half an hour time for Q&A and demo. Okay, so let me start with the demo first. Okay, so you guys can put your questions of ROS related question, obviously, in the chat box. Okay, I think we can wrap up this session. Now I'm just planning to show you with some interactive simulations with some capabilities. So guys, you can just start asking. Maybe you can comment, or you can unmute your microphone and start asking. So in the meantime, I can show you some interactive simulations. Okay. Okay, so I'm planning to show you some demos. So in the meantime, if you have any question related to ROS, let me know. Okay. Okay, so I'm planning to show you several demos. mainly the navigation and manipulation. So first, I will be starting with the manipulation demo. Okay, that is the robotic arm, basically. So this is actually Ubuntu 16.04. Most of the demos are working in this. Let me show you some of the capabilities that we can do with ROS. So this is actually a simulator called Gazebo. Okay, so you can see a robotic arm here. It's called UR5, Universal Robot 5th version. Okay, and what I'm trying to do is I'm doing IK using ROS. Okay, so I'm performing IK on this simulation. I don't have the actual hardware, so I'm using the simulator. So you don't need to worry because these are all higher end topics. So I just want to show you these things are possible using ROS. Okay, let me start interacting with this robot. Just a second. Okay, so we have the robot here and we have the visualization here. Okay, we have the robot. Now I'm planning to interact with this robot. I mean, the tip of the robot is called end effector. So I'm just planning to interact with the end effector. So now I am just setting the goal position of the robot to this pose. Okay. Now I'm creating an IK solution. Then I'm executing it. Okay. So this is actually executing in the simulation, but if it is a real hardware, it will also execute in the real hardware. Okay. So this is a simple demo using ROS. That is manipulation demo. Okay. You can find the robot is moving in the simulation. So I can simply set the goal position or the end effector position, then plan and execute. So it will do the IK and everything. Okay. So guys, any questions? If you have any question, let me know. I know it's a bad timing, like 1:30 to 3:30. It's very crucial time for learning. I mean, it's very difficult to learn this time anyway. Like I can show you some interactive demos. Yeah. So this is how we can interact with a robotic arm. Okay. Yeah. Let me know if you have any questions and you can put in the chat box. Okay. Yeah.
Thank you, Lenton sir. Sir, we'll share a screen right now which contains the questions.
Okay.
So can you please stop sharing your screen, sir?
Sure. I mean, is it in the chat box or separate questions?
Sir, we have collected all the questions and we would be displaying the same on screen.
Sure. So maybe before that, I can show you one more simulation.
Sure,
and
sir.
after that, I will come back to the questions. Okay.
Yes, sir, definitely.
Okay. So now I'm just planning to show you a mobile robot. Let me start the simulation first. So this robot is called Husky. It will take some time to come. Just a second. There's a company called ClearPath Robotics in Canada. So that company is actually building this robot. Let me take. I think something not going well. Let's see. So using this simulation, you can see how to do the autonomous navigation. If it is working, let me see. I think it is having some issue. Let me close it. So I have planned 3 demos, one with the robotic arm, then 2 with the mobile robots. Okay. The MIR simulation, I think you have seen the navigation part while we're discussing. That's the same, but I can show you. Let me take this again. Yeah. So this is a simulation, and this robot is called Husky. You can see the robot clearly here. Okay. And what we are doing is we are doing the autonomous navigation using this robot, meaning A to B. Okay. So let's do it. Okay. Okay. Now, okay, so now we can, sorry for that. So now we can just command the robot, like this is a 2D position, and you can see the robot is planning its path. Here you can see the robot is moving in simulation, and this is a visualization of that. The blue color is actually the obstacles. Okay. So if I am just putting in a goal position here, you can see the plan doesn't have obstacle. Okay. It's actually avoiding it. Okay. Yeah. Similarly, if I can publish a path here, you can see the robot is actually avoiding it. Okay. Yep. So this was the demo that I planned. I think 2 demos are fine. I think you got an understanding about the navigation, then the manipulation of robot using ROS. Okay, so these are the 2 important capabilities of ROS. You can use these in your project, research, or even in a product. Okay, cool. So now it's a time for questions. Okay, so if you have any questions, let me know. I think I can stop sharing my screen, and let me go through the questions. Okay. Yeah.
So we'll share a screen shortly.
Sure. Okay. So I hope you can able to see the questions, guys. Okay. So the first question, for a real product, does this framework require a lot of optimization? Yeah, that's a good question. Yes, actually, yes, because there are 2 versions of ROS. I mentioned that there is ROS 1 and ROS 2. Okay. So ROS 1 is mainly designed for research, meaning research and education mainly. Okay, it's not intended for products mainly. Okay, but ROS 1 itself using in products after doing a lot of optimization and customizations. Okay, optimize means, like if a software is designed for research, means that it may not have all the if you are deploying a software for a real product, you have to do a lot of testing, a lot of bug fixes you have to do. So you have to do a lot of things in order to make the code stable. Okay, but the research code may have bugs, and also it may not be properly tested. Okay, so in order to make ROS into a product, you have to do a lot of optimization. And the updated version of ROS is ROS 2, which is actually optimized for products. Okay, but it's still on development. There are a lot of bug fixing happening, but it is well suited for products. So I will say both are suitable for product. In ROS 1, you can put it in a product if you do optimizations, and ROS 2 is ready to go. Okay. Yeah. Okay. That was a good question. So second question is, could you tell us something on Turtleboard? Sure. So I mentioned that ROS is designed for research and education. I mean ROS 1. So how to test a ROS on real robots? You need a robot at least, right? So the turtle board is basically a cheap alternative for learning ROS, cheap alternative robot, I will say, okay, which is having all the sensors that is necessary to perform autonomous navigation and all. Okay, even you can create your own ROS bot, which may be much cheaper than that. Okay, but most of the universities are purchasing Turtlebot, which is a uh, I will say a de facto standard for teaching ROS. Okay, ROS 2, Turtlebot 2 and Turtlebot 3 is there. The difference is that Turtlebot 3 is much smaller and Turtlebot 2 is bigger, and the price is also different. I will be suggesting you to go with the Turtlebot 2 because it's much bigger, and you can put a lot of things on the top of it. Okay, so yeah, so the Turtlebot robot is fully working with ROS, and you can apply your algorithms on it. It's completely working on ROS, and you can write C++, Python, anything. It is having an netbook that is mounted on the chassis. Okay, so you can simply program it and you can see the output in the real robot. Okay, so the third question is, can we easily integrate commercially available hardware modules in ROS? Again, a good question. So the thing is that the commercially available hardware modules include sensors, actuators, and maybe some embedded boards or something. Okay. One problem with the commercially available hardware is that it may not be open. The protocol may not be open. Okay, so in that case, what we are doing is the open source engineers, the developers who really like open source, they will do what they will do is they will do reverse engineering. Okay, and I will say it's not a proper way to create an interface. Okay, so but maybe the hardware may work, but it may not be the exact correct strategy to interface to ROS. Okay, one example for that is Kinect sensor. Okay, so Kinect actually released by Microsoft. It's a commercial product, and there was no Linux driver. Okay, and ROS interface. So what developers did was they created a reverse engineered driver for Kinect. Okay, and it will work smoothly. Okay, so some vendors will already support Linux interface, also ROS support. Okay, you have seen some sensors, right? ROS support a sensor, so that is already available. I mean, that is already ROS interface is already available. Otherwise, you have to create your own driver. Okay, that is something difficult. Okay, so the fourth question, can a haptic feedback interface framework be simulated in ROS Gazebo? Of course. So in a haptic feedback, what we get is the XYZ roll PTO value, right? Basically, using the haptic interface, we are giving a pose value, right? XYZ, the translation and rotation. Okay, so that input can be used for maybe moving a robotic arm. Okay, and the haptic interface, I mean, the feedback from those devices can also be retrieved But for that, I think I need to check whether there is an existing interface already available, packages available for that, but that is also possible. Okay, you can write a program if there is a collision with the environment. Your program will send some feedback to the haptic device. Okay, so that is possible actually. Okay, and I think there are some existing interface already available to interface haptic devices. Okay. Okay, so the fifth question is whether sensor driver interface available in ROS, for example, SPA, I2C, etc. Which microcontroller support? Again, a good question. So how to interface a sensor to ROS? Basically, if a sensor is sensor can be plugged into a PC using a USB interface or something, then and if it is supporting Linux driver, or if there is any Linux driver available, then you can easily write a ROS driver on the top of it. Okay, and in order to interface sensors that is communicating over SPA or I2C, then you can choose a microcontroller board. Okay, like Arduino or STM32 boards or TNC board. So you can interface that sensor to these boards. Then what you can do is you can interface those boards to ROS. Okay, so there are packages available to interface these boards, that is microcontroller boards, to ROS. Okay, so you can retrieve the sensor value to ROS. Okay, yeah. So 5 questions. Let me know if you have more questions. We have 10 more minutes. Okay, if you don't have questions, maybe we can wrap it up. Okay, so the session was basically giving an idea about ROS. We can't discuss more concept because it will take a lot of time. So yeah, and I hope I have conveyed the message, like we can do these much of things using ROS. Okay, so for more read, I will suggest you to check the ROS wiki, also some books. Okay, also I'm doing a course called ROS Developer Learning Path, which is actually like, maybe I can share the link so you will get an understanding.
Thank you, sir. Do we have any more questions coming from the participant side?
So
Any more
I have,
questions?
yeah, so I have shared the link of my course. If you can just check it out. So this course is actually covers almost all the concept of ROS. But actually, it's an 8-month course, so you can understand how much things to learn in ROS. Okay, so in that link you can find a lot of projects that are done using ROS. This course is actually running now. It's a live course. So at the end of that post, you can find the course syllabus and everything. Yeah. So if you have any more questions, let me know. Otherwise, we can conclude. I hope no one is having questions. Maybe we can conclude, right?
Yes, sir.
Okay.
Thank you so much, Landon, sir, for your insightful presentation for the day. We are grateful for the time and effort that you have taken to share your thoughts and experiences on ROS. I extend my generous thanks to you, sir, on behalf of the entire faculty and staff of the Department of Electronics at TIST.
Thanks for inviting me to. Yeah. Okay then, bye, guys. I can share the slide if required. Yeah.
Sure, sir.
Okay then, bye. Yeah. Thanks. Okay, bye.
Thank you to all the participants out there. The sessions for the day has been completed, and we'll see you all tomorrow. Thank you so much.